very good morning to all dignitaries, faculty members, organizing committee members, and our audience from across the nation who have joined us with an online conference, AstroRetreat 2020. I hope I'm audible to all.
Yeah. Please go ahead.
I, Dr. Bindya Arora, on behalf of Guru Nanak Dev University, Amritsar and University Science Club SciRox, extend a warm welcome to you all. A COVID pandemic profoundly came in most unpredictable form and hence rendered the entire system ineffective. The entire education system had to resort to online measures in order to keep up the learning momentum. The Science Club of Guru Nanak Dev University, SciRox, to embrace the approach to put a firm foot forward and organize a number of web sessions with many in pipeline. This time, SciRox has teamed up with another club, Stellar Universe, run by students of Delhi University, to bring to you an online presentation come talk meet AstroRetreat 2020. It's an online platform for students and enthusiasts of astronomy and cosmology to showcase their work in this field. We have received overwhelming response from scholars from all over the country and abroad, and over 400 participants have registered for attending this event. From a number of participants who registered for oral and poster presentation, we have selected 13 oral presentations and 21 poster presentations. Our guests of honor for today were Dr. Jaspaal Singh Sandhu, the Vice Chancellor, Guru Nanak Dev University, Amritsar. But due to some reasons, he couldn't join us today, and he has sent his good wishes to all. To support us with their benign presence, we have amongst us Dean Academic Affairs, Dr. Sarabjot Singh Bahl. Sir, I request you to kindly say a few words to our audience.
Thank you, Bindya, for letting me in and giving me this opportunity to join this seminar. Well, let me share with you that astrophysics, and there are so many other aspects that you've mentioned: cosmology, high energy physics, quantum mechanics, astronomy, though they are not my core fields, but I've been really interested in them right from the day when I started reading Stephen W. Hawking of time. So I like to follow whatever is happening in astrophysics, but as a layperson. And I think this is a great initiative that you have taken to host, this kind of. I'm sure that this seminar would be more or less in a layperson's language, which people like us also can understand. And the young people who are not even deeply involved with the subject of physics will be able to get the gist of what you're trying to say. And I feel popular physics is a very, very popular medium, is a very, very important medium to invoke the interest of younger generation. And for other people also, because I feel that I think the way science connects you to the wonders of the universe, to the principle of Satyam Shivam Sundaram. Can you hear me?
Yes, sir.
Yes, sir, we can hear you.
Okay. The truth, the goodness, and whatever is beautiful in the universe, I think science plays far greater role than any other philosophy or any religious scripture. So I again congratulate you for having organized this beautiful seminar. And I'm going to sit here throughout and listen to whatever enlightens me. Thank you very much for having me on the board. Thank you.
Thanks a lot, sir, for honoring us with your presence and your words. Any student activity is incomplete without the guidance and presence of Dean Students Welfare. Dr. Hardeep Singh, I request Dr. Singh to address our lovely audience.
Thank you, Bindya. Thank you, Venus, for giving me this opportunity to be with you this morning at the inauguration of this conference. For those people, I also welcome Dr. Bahl on this occasion for the inauguration of this particular thing, the inauguration of this particular conference. As has been pointed out by Professor Bahl already, that the topic chosen for this particular conference is extraordinary in the sense that the latest interest of all the scientific communities towards this space. Let us look at the kind of activities being promoted by the government of India also, like we had the attempted landing on moon very recently, and the kind of launches that we have in terms of various satellites and all. So there's a renewed interest in the space sciences, and it is for the betterment of the mankind. In fact, a few things that we cannot do here, probably it's very easier for us to carry out in the space, and there are many things that still need to be explored. So this is a great idea to organize a conference of this nature at this particular juncture, when everybody is so stressed out with the time that we are passing through, and we are using this kind of a medium to integrate the various participants spread across the various continents. In fact, when I was looking at the list, people are from Australia also and from other countries as well. They are joining this particular conference. So it's a great effort, and I appreciate this kind of activity. Needless to say that these kind of activities have already been done very actively by this particular club under the mentorship of both of you, like Dr. Bindiya and Dr. Venus. And I hope these type of activities will continue to come in the rapid succession, the times to come as well. So I think the participants are going to be enlightened with the, to begin with the talks of two very prominent speakers that we have, Professor Avinash and Professor Jasjeet. And then I see the very comprehensive list of presentations that we have in terms of papers and oral presentations, poster presentations. So overall, it's going to be quite an effort. I mean, it's going to be quite a comprehensive effort. And I think this is going to be beneficial for all of us. As Professor Bahal mentioned a little while ago, that probably this is going to be something in the layman's language, so that many people who are actually not in the field of astrophysics and cosmology or cosmology, they actually understand the finer concepts of these particular areas, and we are able to rope in much more number of students and active, say, interest partners in this particular group as well. So I think it's not the first case that we are going to have this conference and then sleep over. But I sincerely feel that with the kind of interest that we have, we are likely to have much more conference in this particular domain also. I mean, not only the other domains of physics, but this domain is going to be very popular, I personally feel. So my best wishes to the organizers, my thanks to the participants, and especially the eminent speakers, Professor Deshpande and Professor Jasjeet Singh, for having agreed to our request to be part of this particular conference, and hope at the end of the day, everybody is enlightened with the concept, the kind of talks that we have, kind of inquisitive things that we are looking into. All the best. Take care and enjoy the conference. Thank you very much.
Thanks a lot, sir, for taking out time from your busy schedule and for your motivating words. So we also have amongst us Professor R.C. Singh and Professor Seni. I really thank you, sir, for taking out time and being here. They have always been a supportive pillar throughout. Now let me present a brief introduction about the two science clubs who have taken an initiative to organize this conference in collaboration. So Stellar Universe is an initiative by students of Dayal Singh College, Delhi University. The main motivation behind their idea was passion for science, scientific research and enhancement of knowledge in advanced topics like astrophysics, general relativity, etc. This small group of college friends soon grew into 500 plus strong network of science enthusiasts across the nation and abroad. With immense help from institutions like Nehru Planetarium and guidance from experts in the field such as Dr. N. Ratnashri, Director of Nehru Planetarium, Dr. Neeraj Saxena, Advisor AICTE, and Dr. Shibesh Kumar, Professor VIT, the club has reached new heights. SciRox is a science club of Guru Nanak Dev University, and it's a very fruitful initiative taken by our worthy Vice Chancellor, Dr. Jaspal Singh Sandhu. SciRox is a student-run club with the purpose to promote various scientific activities among students. And I'm really grateful to our Vice Chancellor for taking this initiative and inculcating this feeling of student-run clubs so that they can collaborate and they have a common platform where they can talk and then discuss their social and scientific concepts. So the key goal of these clubs are to develop scientific temperament, increase collaboration among students, and provide a common platform for students' interaction. Without any further delay, I would like to start the conference, and I can see here our first speaker for today is already here, Professor Deshpande, and I would like to invite our first chair of the invited session, Saurabh, to kindly introduce our first speaker.
A very good morning to everyone present here. My name is Saurabh. I'm from Stellar Universe. So for our first session will be by Professor Avinash Deshpande. So Professor Avinash Deshpande is an Indian astrophysicist. He was a professor of physics at the Raman Research Institute, Bangalore. He's credited with the development of a receiver for high time resolution studies of pulsars at low radio frequencies. He has contributed towards the studies of pulsar magnetospheric emission regions and in the elucidation of unphysically ultra-dense neutral hydrogen irregularities in the interstellar space. He was born on 23rd of January 1958, graduated from IIT Kanpur in electrical engineering branch in 1980, and then he earned his PhD from IIT Bombay. He also did his postdoctoral work at University of Tasmania during 1990 to 1992. Currently, he is affiliated to IUCA and IIT Kanpur. He has been involved in a number of projects, including the Skywatcher Network, the Indian Swan, a collaborative student science radio astronomy project, apart from many others works undertaken by RRI. He was also awarded with Shanti Swarup Bhatnagar Prize for Science and Technology by CSIR, which is one of the highest Indian science awards for his contributions to physical sciences in 2002. So now I'd like to hand over the stage to Professor Deshpande to take over his talk.
Thank you, Saurabh, for those kind words, and thanks to the organizers for giving me this opportunity to talk to all of you and the youngsters who will be attending, I'm told, across the world. I will try to share the excitements associated with the fields in which most of us are busy using the radio techniques to look at the sky and understand what is going on. I should be able to share the screen now, right? Okay. All right. So that's the formal title of my talk. I think just to save bandwidth, I will disconnect my video for let's see if I can do that. My stop video, yeah. So that because I have limited connectivity, I don't want any interruption due to that. I hope I can be heard.
Yes,
Yeah,
you're audible.
You're audible. Please continue.
Thank you. So I'll proceed. I will be trying to introduce us to the field of radio astronomy. Astronomy needs no introduction. Even most of you might be even familiar with the radio astronomy aspects. So the idea is to see how we probe the radio sky, what are the techniques and challenges, and then I will go on to describe a recent initiative that involves youngsters across all educational institutes in India, and describe at what stage this initiative is presently. Okay, I'm sure all of you are familiar with these views, which are that that we can see with our own eyes and with the help of optical telescopes in cases of objects which require zooming onto them and so on and so forth. So I'm not going to spend time describing them. They're all familiar to you in one context or other. There are objects nearby, there are objects far away, all the way extending to the beginning of the universe. In general, not only the radio astronomers, but astronomers' measurement agenda is very simple. It can be stated in somewhat trivialized words. One is trying to measure intensity or number of photons as a function of direction, and the direction requires some specification of which part of the sky plane you're looking at. So it's a projected two-dimensional sort of spherical shell. And we also want to know what color the light has, along with its intensity, and whether things are constant or changing in time, whether the intensity is changing in time in some way. Of course, if we are lucky and have resources, we would also like to measure additional details in terms of polarization state of the received signal. So of course, there are two main entities associated with each one of these. One is, of course, the resolution, the fineness with which we can make these measurements, say in intensity or in direction and frequency and time and so on, and the span over which we can gather this information. And these two numbers specified for each one of these entities will sort of define an instrument in some sort. So of course, we want, as we will see, we want best in each one of them, and we will see what comes in the way. But it's of course an engineer's delight to deal with the challenges, and lots of advances have been enabled over the last 90 years of this field. What we are looking at, of course, is this electromagnetic spectrum, the one end of the electromagnetic spectrum, namely the long wavelength regime, which is orders of magnitude longer wavelengths than we encounter in the visible wavelength. And so microwave radio and even millimeter, sub-millimeter waves, which sort of begin to occupy the electromagnetic spectrum just below infrared, are all considered in the radio regime in principle. So various instruments are there to study various regions of this electromagnetic spectrum. Some require us to go to the space because the atmosphere or ionosphere blocks the radiation from reaching us from the sky. And so those are catered to by sending appropriate spacecrafts. The stuff that reaches us, of course, can be studied from the ground. And one didn't know for a long time that we actually have radio signals coming from the sky till Jansky's discovery of radiation from the sky while working on a communication system that he was developing for terrestrial communication. He noticed some disturbance which repeated at the same sky time, not the solar time, which differs by about 4 minutes a day. And so it's like, you know, looking at the distant sky, which repeats at every 23 hours, 56 minutes. So he noticed that difference, and that's how one could attribute that this is some signal coming from the sky. Of course, the main advantage, as it turns out, which I will keep on re-emphasizing of the radio eyes, is that we can see through the dust and hence farther. And this was a big breakthrough from the way we were limited in optical wavelengths due to obscurations that I will show the effect of next slide. But before that, let me mention, although Carl Jansky is called the father of radio astronomy, the real mother of radio astronomy is Gro Trieber, the first radio astronomer, really speaking. And he always, you know, called himself amateur astronomer, and he remained amateur, and the way he dealt with the in an uninhibited way his exploration. So he, after Karl Jansky could not pursue what he had actually found, this field would have remained dormant, except for Groth-Reber, who in his backyard on his own initiative built a telescope to figure out what exactly Karl Jansky had found and how is it distributed, how does it change with frequency, and so on and so forth. And of course, after many trials, he produced this beautiful first map of the radio sky, which showed the key features that are so prominent in the radio sky. Some of these spatial sources that are marked there on this globe. And but for him, we would have delayed the progress of radio astronomy. Okay, so what we are again emphasizing that we are seeing through the dust, but why? What is so big deal otherwise that radio astronomy should be pursued? We will see that, or has been realized that bright radio sources, which show brightly in radio, did not really have optical counterparts. That means we are looking at something really new at radio wavelengths that wouldn't have been visible at all at optical wavelengths. And vice versa, the brightest optical sources did not have any significant radio counterparts. And so you can see that the importance and complementarity of different regions of electromagnetic spectrum. And so there are, large number of things to be studied, which were yet not known to us. And so the radio window really allowed us to explore things in an entirely different way. And of course, one could also check the correspondence with what is already known. So this is the, sample image of the sky made with very low angular resolution. But this is how the galactic plane would look like in radio with 2 or 3 prominent sources which dominate the radio sky. If we look at, this is just to emphasize the differences we see at different wavelengths or different parts of the electromagnetic spectrum. So this is a collage made of measurements made in the strip containing the along the galactic plane of our galaxy. And although in the sky it appears oriented in certain ways, it's artificially straightened here for the convenience of viewing. You can see that radio distribution, brightness distribution or intensity distribution is very different than what you see in optical wavelengths, where a lot of obscuration due to dust is pretty evident. In fact, that is borne out by the fact that infrared shows the dust presence also corresponding to the places where you see obscurations. And then, of course, X-ray shows a completely different view of that part of the sky, and so does gamma rays. So there is motivation for studying each piece of it. And to really understand something, you really require an approach where you put in all possible clues that we can get from all possible methods and tools and regions of electromagnetic spectrum. And nowadays, as you know, it's not even limited to the light. It is a multi-messenger astronomy era, which quickly took over the multi-wavelength era that I was just describing. So, of course, the reasons for why we see different things at different frequencies are tied up with a variety of things. One among them, of course, is the nature of the radiation. We are familiar with the black body radiation, which, depending on the temperature of the body, the peak emission occurs at certain wavelength. And the radiation, that's what shows up predominantly in optical wavelengths for the typical temperatures that we encounter in stellar context. And whereas there is a lot of emission coming from non-thermal processes, predominant among those are the synchrotron radiation, which occurs when relativistic particles gyrate in the presence of magnetic field. And that emission is seen to increase towards the lower and lower frequencies, and very dominant contributor in the radiation that we see at these very low frequencies, particularly radio frequencies. So that's what we largely see. We of course see black body radiation of different kinds, but it is rather weak because we are in the Rayleigh regime of this black body curve for most of the sources, most of the temperatures. So this is how the radio images would look like. These are some examples, and I would like to, I'm showing them for two reasons. One is to show that this is the sort of all sky map. When you zoom on to a tiny part of it, you will see details to the level of, which are comparable to, stellar distances and a few parsecs and so on and so forth. And of course, you can study individual objects in detail. This is the galactic center, which has beautiful structure, which has been resolved with very high angular resolution using the most modern telescopes. You can see other objects as well, but all these objects, when we look at these images, unlike in the optical wavelengths, where we can actually put our eye to the eyepiece and look through the sniff light from the telescope while it's making measurements at its focal plane by putting photographic plates or CCD cameras and so on. While it does that, we at radio are observing just one point at the most in each one of these images. And we will come to that. To make an image, a lot of processing has to happen at radio wavelengths, unlike at optical wavelengths. No radio image is accessible, although it's formed in principle, and certainly it will have limited angular resolution. And to really get these high resolution images, we need to do lots of other things, which I'm going to partly describe in the rest of my talk. So this is another beautiful image of a quasar, which has this very tiny core, which is to resolve or see which this could be seen only with telescopes of the size of the Earth, and how those are built is something that we will allude to in the rest of the talk. There are some point-like sources which we don't see as sources as a dot with the kind of angular resolution we have. We can't really resolve them. We can't see any details in them, but we receive signals from them as a function of time. We hear ticks from them as modulations of the radio waves that they emit. And these, as you know, were discovered by Jocelyn Bell while she was trying to study twinkling of distant radio objects using the scintillations that occur in the interplanetary medium, the medium within our solar system. And so this was accidental discovery and has led to profound understanding of several aspects of the constituents, particularly the compact constituents of our universe. Another aspect that had had a major breakthrough in our understanding and the way we can explore our universe is the H1 neutral hydrogen 21 centimeter hyperfine transition line, which occurs at 1.42 gigahertz. And this suddenly allowed us to study the motions of objects and regions that have this material. And suddenly this opened up several things. One of the first things that it hit us with was the presence of dark matter, and something that we still do not understand within our galaxy, outside, in other systems, bigger systems across the universe. Another landmark observations in radio was this detection of 3-degree cosmic microwave background, which was accidentally discovered, again, like Jansky's discovery, where they were trying to do some test with their antenna and found that there is no cooler part of the sky than about 3 degree Kelvin. And that led them to this discovery. And then lots of detailed measurements have been made. Things have been measured to a few millikelvin level as the background intensity variation seen in the cosmic microwave. And that has profound implications for our understanding of the universe and its beginning and subsequent structure formation. So the emerging picture, as this you would have seen in all popular renderings of this subject in astronomy in general, is the people believe that there was a big bang, and then there was this afterglow light which came in form of cosmic microwave background, and then there was this dark age when everything was largely neutral, and then the first stars formed and they started reionizing the material around them, and progressively the entire universe. And various entities were formed to make that happen in the first place, and things have evolved since. And this is where we are after about 13.7 billion years later. So I will not have a chance to go through any one of these aspects in any detail, but I will concentrate on how people try to measure it, and what are the challenges and what the foundations or pillars of these measurement techniques are. So again, reminding us, we are trying to measure intensity of the light received, regardless of, this is not limited to radio astronomy, this is limited to measurements in general of, what we are after is intensity. We want to know which direction it is associated with, what is the color, how does it change, or is it stable? And as I said, the two entities, resolution and span, in these decide the complexity of the instrument. So one of the major differences, I already mentioned one of the differences, where I said we cannot see the image as directly as we can see in optical wavelengths. One of the major differences, which is simply to do with the wavelength at which we are dealing with, is the photon energy. The photon energy is more than 1 million times smaller than what we encounter at optical wavelengths, typically in terahertz regime and higher. And so these photons are too weak to be detectable individually. And they cannot cause any reaction to a detector. So we really don't have any detectors, known detectors yet, unless some of you discover them in the future, as we have in optical wavelengths. So there is no reaction occurring. There is nothing that changes in the material at some basic level. But we can appeal to the feeble motion or the dance that the incident electromagnetic radiation would induce in terms of motions of electrons corresponding to the changes in the electric field of the electromagnetic wave. And so if if we have large photon density, we can sense this signal and we can amplify it and record it. And that's the only way we can receive and sense these signals at radio waves. So the transducers for incident radiation field at radio frequencies is really the piece of metal or something where the electrons are allowed to freely respond to incident radiation or external electric field of the electromagnetic radiation. And so, of course, we require these things to be amplified hugely before we can even record them. So to do that, a variety of structures, metal structures you will see. You will see aerials of different kinds of horns. What you see are shaped reflectors to collect the light, focus it at a convenient location where this sensor is put. So this is not the sensor itself. This is a collector, and then the sensor will be at its focus. So there are several familiar examples of this that you would have encountered. What we are really looking at is the noise coming from the sky. We call it signal, but it's really pure random Gaussian white noise. What we mean by this, can we visualize it? You would have visualized it in some way when in olden days, the TV stations used to be switched off, and on your TV screen, you would see a speckly pattern, bubbly pattern, which is changing continuously, randomly. So the stuff that you see there is really the description of the kind of noise we are talking about. And what we are interested in is the variance or the magnitude of that variation. So, so this is the sky noise which brings us the cosmic news. Unlike in communications, where the signal and noise have a clear distinction. We transmit something, and then there is some unwanted stuff that gets added and that we call noise. Here also we can adopt that strategy of what is signal and what is noise. We can say what we want of that noise we are getting from the sky is our signal, and rest of it we can treat as noise. And that's what we generally do when we commonly sort of call something signal and something noise. So the noise properties are necessarily statistical. They have color. This noise has color, which of course we can describe its probability density function to describe the statistical property. We can describe a spectrum to describe its color. And if they have any coherence properties, spatial or temporal, which we can describe. So all these entities become relevant in the sense we measure them. Now, photons that we receive, regardless of whether they are radio or other wavelength photons, they follow Bose-Einstein statistics. And this is a combination of two random processes, naively stated. One is tied up with the expected number of photons at any given time. And this is what the prediction will be, where the average expected number of photons in a given wave packet, a given wave front will be described. And this itself is dancing up and down. So different shells of photon delivery emanating from a distant source contain different number of photons. And those numbers changing from shell to shell are described by an exponential distribution. And as you can see, that's a pretty long tail distribution. The nice thing about that distribution is the mean expectation of number of photons is equal to the standard deviation. But it's also bad news. That means the amount of fluctuation occurring is as much as what we are trying to measure as a mean entity. While this is for the intensity and number of photons, the real and imaginary parts of the field, which we have the privilege of measuring at radio wavelengths, follows Gaussian distribution, pure Gaussian random distribution. And now, given that each one of these wavefront has shells, has so many numbers as given by the exponential distribution at any given time, one realization of it, we will see that the actual number we will receive per unit area would be different from one person's collection to another person's collection, even if the area were to be same. And that number change occurs due to a Poissonian fluctuation, and that has the mean equal to the variance. So you can actually have wild variations in the number that we receive. So we are stuck with this random process. We're trying to detect something, which is the mean number of photons. And that number is fluctuating madly for two reasons. One is because each shell itself, at each time reaching us, itself has different number of photons. And even if when we try to do similar measurements simultaneously, we will receive different number of photons due to Poissonian fluctuations. We are finally trying to, through all this difficulty, trying to get the mean number. Okay, what is this number typically? Which one of these fluctuations are important? So we will, as we will see, what is called the wave noise, the exponential distribution is the most important one at radio wavelengths. And that, of course, depends on the photon occupation number. This is an example of a black body curve. And along with that, the occupation number is shown, which is this exponential factor that we encounter in the black body Planck formula. The example shown here is for the weakest of the radiation that we see in the sky, the black body radiation at 2.7 K. And you can see that number increases gradually towards the radio frequencies, even for this weakest of the radiation. And it's in tens and thousands and so on. And so this is in the occupancy in the phase space cell. And of course, if you have large collecting area and signals coming from various directions, you can see that you will be bathing in photons. So we are always showered by radio photons in abundance. Okay, there is no dearth of radio photons coming from the sky. So we are always in the regime of large number of photons, and what it means is the variance of the fluctuations are dominated by now the wave noise. We don't have to worry about how much difference occurs between one person looking at, with bucket here and another person looking at similar size bucket there. The numbers are not going to be too different, but they will receive different amounts at different times. And now this correlation is a very powerful one. And this allows us to explore the coherence or the correlations between signals received at two locations. So one important side remark to this is that the sky is not dark at radio at all. Even the feeble microwave background ensures that the occupation number at most radio frequencies is already high. In other words, even though the particular contribution to the signal we seek might be very weak, there might be a tiny source which is so weak that it gives only a photon or two once in a while. It's already buried in the classical sea of noise that comes from even this background radiation. And the benefits that come with it should be harvested. And we do that by, trying to measure something, some precious quantity called phase of the signal. And so first thing is we can use the This is just an example of how the occupation number is different for different sources. Just stressing the point, giving specific examples. I will not spend much time on it. So the essential picture emerging is that at radio wavelengths, we have packets coming delivered to us from the sky in large number of occupancy of each bogie, while it was the case B for optical wavelengths from, photons were rare, not all bogies, all phase-space cells were carrying enough photons. So we can use wave description safely, and one of the entities that becomes really possible to measure and exploit is the phase information. So now we can go and actually measure not just the intensity, we can measure the electromagnetic field, which is the major difference and advantage at radio. And we are blessed with that, and it has been exploited abundantly. I will not go into the detail of why I was calling this Gaussian random signal, describing the fields, and that can be arrived at through various considerations, sheerly appealing to central limit theorem, given the large number of contributors to the signal that we receive or the noise that we receive, and their uncorrelated nature. And you can convince yourself that even a small sector in the universe that we look at, large number of contributors of radiation would be there, and they are not talking to each other. And so the sum total would necessarily follow Gaussian distribution. So this is, again, to come back to our main agenda, the number of entities we want to measure are about 6. And in each one of them, we would like to have the best. We want very high resolution in each one of them, and we want the widest span. This is what we exercise as our choices when we go and buy, for example, a mobile phone for ourselves. We say its camera should have, a wide angle, as wide an angle, and as high angular resolution. So that is typically these days specified in terms of megapixels associated with the camera and so on. So we also want large number of megapixels. We also want large color gradation and so on and so forth. But the trouble is that while it's possible and up to a certain extent within the regime of our greed, it can be met in optical wavelengths. We see that it cannot be met at radio wavelengths, because at some very basic level, each one of these grid items cannot be defined mutually independently. So there is always a compromise, and that compromise comes from uncertainty principle. We are not allowed to ask more detailed question in any one of the aspects if the other one was already specified or chosen by us or ambiguous to a certain level. So you can understand this in terms of Fourier pairs and basically position, momentum, energy, time, and similar thing can be translated into other relevant pairs of angular response and aperture distribution, brightness distribution, and spatial coherence function. Spectrum and temporal coherence are well known, and so on and so forth. The essential thing is we are dealing with Fourier optics or Fourier aspects and Fourier pairs in one context or another. And as you know, the width, if it's broad in one domain, given function, it will have a narrowness in the other domain. And that inverse relationship is what stops us from getting combinations that we would have ideally liked to have, but are not possible due to fundamental limitations emanating from the Heisenberg uncertainty principle. Now, these considerations are unavoidable and relevant even for a single photon case. And you can convince yourself of this by taking a single photon and taking its x momentum if the aperture is extended along x, and see write down a momentum uncertainty and position uncertainty and the product of it, how that is limited by the Heisenberg formula, and work out an effective limit on the ambiguity that you will have to live with in terms of the direction of arrival of the photon. And similar thing about the other pair. So you can reach your diffraction formula even from consideration of simple uncertainty principle. Okay, so as we have seen that we have no detectors, we need sensors, and antennas are an integral part of any receiving system that we have. We have filled apertures, that means continuous apertures, buckets which collect these lights, and or we can have different sensors and ask them to work in tandem, and essentially we collect the signals, and what we have is a equivalent single pixel camera. And now that's pretty pathetic. We have just a single pixel camera, while in the this technology regime we deal in optical wavelengths with megapixels. And so traditionally radio astronomers have been living with this single pixel camera, and the single pixel camera is moved into different directions, and we produce a raster scan, and this is how we used to make images in the olden days. Things have slightly become better now with the advent of many telescopes. These are range of telescopes. I'm not going to go into details of that. And this, all that I was mentioning about this focal point, which has one pixel camera, which can be a line or a point. And that's only that much was possible in early days. Nowadays, people have learned how to build a multi-pixel equipment at the focus, and people have been able to make simultaneous measurements in different directions, and not yet anywhere close to the kind of megapixel ability by putting something at the focus, but one can make megapixel images using a technique of synthesizing an aperture, or synthesizing a situation that we are so used to in optical wavelengths. But before we do that, the signals we sense by the antenna are so weak that we have to amplify them by orders and orders of magnitude. And while doing that, we have to pay a price. Nothing comes free. While we want to boost the signal, we will also have to pay the commission of letting the equipment add its own noise to the to what feeble light, feeble signal that we have received from the sky, and that makes it harder. We try to get the best deal by using the most cooperative equipment, which adds very little noise. But there are quantum limits which are not relevant at radio. I just want to emphasize that they would be relevant in optical wavelengths. That's why optical wavelength amplifiers, coherent amplifiers, are not very popular, whereas they can be used routinely at radio wavelengths without too much of extra cost. Of course, standard considerations of maximum power transfer and so on have to hold good. And this is true regardless of whether it's radio astronomy or otherwise. Even while I'm talking to you, unless we have good matching of impedance, what I'm saying may not reach you well. Even this communication channel Zoom that we are using has to allow that the maximum power of my communication to reach you, and so on and so forth. So I will not go into details of this. All that we require is a very linear system. That means very reliable system which does not modify or distort the information. So we need system with low distortion. And one way of stating it is that we need a linear system, which only multiplies the input by some constant and produces an output, which is authentic replica of the input. Now, it turns out that most of the, or almost all the linear systems, physical systems, perform what is called a convolution in the process. They have, if you poke them, the response that they have is what they repeat for every poke you give, regardless of the size of the poke and when you give it. And that's the hallmark of a linear system. And so what we are getting is the system does not behave differently based on, its behavior is not different based on the input. Of course, it will produce the output proportional to the input, but in a manner that is treated identically regardless of the signal. Of course, finally, we want to detect the signal from the sky, and the best technique, as we know, which is being talked about in much more loudly these days in the case of gravitational wave detection, what we call MASH filtering. So what we want is this convolver to act as a sort of detector of a certain pattern. If we want that, we make it like the lock and key. If we want to see whether this is the right key, we make a lock for it. And or if we want to see if the two locks are similar, we make a key for one and see if the same key opens the other one. So we have to use a conjugate technique to detect a particular pattern. And so that's what the heart of MASH filtering is. How sensitive measurements we can make depends on the number of photons, depends on the number of photons we collect, and the number of, as we said, now each one of these measurements that we make is wrong by 100% because the standard deviation is equal to the mean. And so it's like asking 10 friends about something, and each one of them will tell you some truth, but equal amount of lie. How do we make out what the real truth is? Thankfully, they will have the same amount of lie, or same amount of lie, but different types of lie, whereas the same truth in each one of their answers. And so we can ask large number of our friends, and a mean inference from that will have less uncertainty. And this is the basis for the way we make measurements and make more and more accurate measurements. And this is captured by the number of independent pieces of information we can get, or a number of friends we can ask. And that is decided by the amount of bandwidth we can use. Basically, the number of samples, number of people we can encounter per unit time, and the amount of time will tell us number of visitors and the number of questions we can ask to different individuals. And we collect all the answers and take the mean, and this improves our ability by square root of the number of such independent samples. I will not go through this. This is just a cartoon to emphasize how we can reach different regimes and how at optical wavelengths we can continue to gain by making bigger and bigger telescopes. Okay, I will not have chance to go into any detail of coherence and correlation, but we will be trying to measure coherence in the signal, and the technique for measuring coherence is correlation. Now, we know that when we see no correlation does not mean there is no coherence, but certainly if there is coherence, we will see coherence in certain regimes when things are really brought to the same level, same footing. So, but certainly if we have incoherence, there will be lack of correlation. There's no way you can get correlation in the absence of coherence. Okay, and this is the principle that is used to construct big telescopes. As I said, we can now make megapixel images thanks to this basic principle, and I'm not going to go into details. What we can measure is how signals are similar at two locations is decided by what is the brightness distribution in the sky. And it depends on the level of similarity. It dictates the level of similarity we will see at signals received by two people standing at two different locations on the Earth. Their exact locations are not important. How they are separated with respect to the radiation source is what is important. And so by you will find different measures of similarity will be obtained when the orientation of the line joining the two people is changed, or their separation is changed. And this allows us to now construct an image of the sky as if we had a big gigantic telescope where we received let's say tens of kilometers size telescope, and we received radiation from small pieces of it. Let's call it E1, E2, E3, E4. And then what we are interested in, the sum totals modulus square of the electric field. And that, if you expand this sum within this modulus square, you will find that you get terms like E1, E2 star, or EI, EJ star, like entities, and they are basically the pairs of information. I mean, this is the pair product that you can measure with pair of antennas. And so if you have n antennas, you can have NC2 baselines, and suddenly you can also use Earth rotation, and putting all this information together, you can begin to make images. The basic principle involved is nothing but the Young double slit experiment illustration. And if you understand that in all its detail, you would have understood everything that goes on in radio interferometry and synthesis imaging. So the only thing I would like to remind is it works even when we record the two signals in the two locations, and thanks to the indistinguishability of photons. Remember that in most cases we record the signals routinely, and then so you will have fringes and terminologies like that encountering. You can get, you can make measurements across an imaginary size of your dish in regions that are marked here by ellipses. And you can measure the similarity between the signals received at with separations and orientations given by this. And when you get this information and Fourier transform, you will begin to get images of the sky as a Fourier transform. And that technique has allowed us to study a variety of details, a variety of regions in the sky at great details. And these are some examples at various frequencies. You can see the even nearby sources in certain detail. This is the supernova remnant, as well as a very fascinating source. This is the center of the galaxy that I had shown. You can see this great details at various resolutions, zoomed in using different instruments, basically reaching the size of the Earth as the size of the telescope to get details at the level of a few light years, many kiloparsecs away. Okay, so the quest for bigger and better and more sensitive instruments to probe things deeper, the sky deeper, continues. And we have many instruments coming on the horizon. And one of the major issues is that we have interference created by local man-made sources, and those we need to move away from. And that's why some of these instruments are coming in areas where there is no FM signal, but there's no hiding from lightning and other natural polluting sources. Okay, so this is the SKA. It offers very challenging opportunities to younger generations and so on. And in this, not in the same breath, but on the Indian scene, there is an initiative called Skywatch Array Network, And this was initiated at the Raman Institute. This was prompted by the story as it developed from 2007 after a discovery of what is called the fast radio burst, which is occupying large radio astronomers' mind these days. But in general, the realization that the sky is not steady, there are phenomena occurring and changes occurring in the sky light or in the universe, and can be probed through the light that reaches us through its variation all the time on various time scales. And so this is a new aspect that has allowed people to invest time and effort and getting rewards for making now more regular monitoring measurements of the sky. I will go through very quickly what is SWAN, why, and how we are trying to realize it. As I said, the story began in 2007 of the radio transients, prominently as sort of very magical sources of light, which showed single dispersed pulse and nothing else. And of course, it implied that this light must be coming from very distant objects, given the amount of dispersion one had seen. And that can be seen because the light, after having traveled through ionic medium for long distances, develops some amount of retardation as you come to lower and lower frequencies. So different color vehicles arrive at different times, and from that you can make out how the speeds differ for different color of vehicles. And you can make out how many electrons it encountered on the way. And so that tells us that these light must be coming from very distant objects. People talked of terrestrial origins of it, and which were actually, this claim itself was a mistaken claim for something that was created by some microwave oven, which was later understood. But the true signal, this is an example of it. A beautiful dispersion track seen over extending over a second or something, and very bright signal given the fact that it has traveled so far. So people expected such events to occur several hundred per day, and about that time in 2013, about 20 were known. But there was a rejuvenation of this activity since then, and these were claimed to be of cosmological origin, coming from distances of gigaparsecs or gigalight years. And lots of things have happened since. I will not have any chance to go through the details. There's several talks worth of material here. But they were first repeated such burst seen from one of the directions, from Arecibo. Now there has been one seen from a galactic source called Magnetar, and the mystery is deepening. And thanks to the new telescope called CHIME in Canada, which has multiplied these detections to the level of several hundreds. And but of course, we need to distinguish this from anything that we make. And the best way to do that is to locate ourselves at multiple locations where the environment of man-made signals is very different, instead of going to remote places. And so the idea is to go to educational institutes which are located at different places, and use an appropriate instrument at each location with large bandwidth, and exploit the power of how the signal appears differently in different frequency regimes, and use that as a distinguishing characteristics for confusing signals. So of course, this is how signals can be detected. Each one of these delay tracks can be traced differently. I will not go into the details of this. This is a much more involved figure, needs a lot of explanation. But that two objects can be detected, for example, even if they are in the same part of the sky, looked at by one instrument. So this, right now we see that this is one of the motivations. The other motivation is that the best instrument we have in India is the GMRT, which gives us 25 kilometer size synthesized aperture. We have not yet ventured into VLBI in a routine way, very long baseline array. And so with these two things noted and essential drivers, we have embarked on Indian SWAN. And the third important aspect of SWAN is to train, involve, and provide hands-on experience to a large number of undergraduate and postgraduate students in all aspects of SWAN through their direct and active participation, starting from even the design stage, and doing research using this array network. So the eventual network is proposed to have a bucket at each location of the 1,000 square meter area, which would be typically 30 meters by 30 meters or 100 foot by 100 foot kind of area, and working in a very wide frequency range of 50 to 500 megahertz. As a first step towards it, to establish credibility and show that it can be done in principle, a phase 0 setup has been realized at Gauribidnur, one of the observatory sites maintained by Raman Institute and Indian Institute of Astrophysics, where available equipment was hooked up to realize 8 station equipment, which can be relocated at 8 different sites across India. And then serious observations can be conducted in this VLBI mode, even including using GMRT as one piece of it. And in the first phase, post this phase 0, one wishes to increase the aperture from what small aperture right now we have. The present aperture is of the order of about 20 square meters maximum, and 8 stations, narrow bandwidth. But this will be then expanded both in terms of size and spectral coverage. And then we will swiftly expand to a fuller set to reach about 40 plus technology and science institutes and universities across India to have this equipment and working together as in tandem to make a big network of telescopes. What this will give in comparison with GMRT, which gives you 25 kilo lambda coverage or dish, it will give you 3 mega lambda coverage. So it's essentially 2 orders of magnitude in each one of the dimensions. So it's a 4 order of magnitude increase in the angular resolution. So this is how it looks right now. These are the small arrays used as single stations. And this has been combined with some equipment we had built for making tomograph of the pulsar magnetosphere. And these have been hooked together. Lots of students have been exposed to this, trained in the process. And this is how the collage sketch looks like of 8 tile system spread across the land in Gauribidnur. Presently, it's spread over about 200 meters. And things are ready. People have been using it, and remote access to student has been enabled. And so lots of things have happened. I will not go into the details of it. There were many activities for students to both get familiar with it, use it profitably. And right now we have preparing for the next phase. We have a Swantena antenna design challenge where 38 teams consisting of about 250 participants are participating across India. And so they will be the ones who will be designing the equipment of this future telescope. I will not go into details of this. These are some test results, which will require a lot of explanation, but this is basically to indicate things are all working well as expected. And we, of course, see both man-made signals as well as what is coming from the sky. the expected performance of the equipment in terms of fringes that we expect to see. We would like to use bigger buckets when possible, which are MST radar, if not GMRT, and default modes of Skywatch have been enabled already. So a large part of the sky is being monitored continuously. People are welcome to come and use that data to make detections like the one shown in this example of dispersed signals. And right now, lots of follow-ups occurred in the times when the initial challenge was declared for imaging, and actually 6 participated teams actually produce actual results over 100 square degree of the sky. So I will, sorry, this is a repetition. And so this is what something students attempted to make measurements over a dish which is populated like this as a sample. And of course, there will be lots of things done. Students will be involved continuously. And finally, when we have this setup moved to different locations across 8 institutes, so we will have a target source of Cygnus A, which is one of the bright sources that we'll try to study. Cygnus also means swan, just by chance. We have been having fun with other issues, including how to calibrate the signal using drones and so on, calibrate our equipment using drones and so on. So there are exciting time ahead, and thank you for listening. I will stop here.
Thanks a lot, Dr. Desh, for such nice informative talk. Radio astronomy is surely one of the most booming fields of astrophysics with the current facilities available and with the future projects that are planned. So with this, I thank you for this nice session. And with your due permission, I would like to ask a few questions that have been posted on the chat box on YouTube. May I go ahead, sir?
Yes, please.
Okay, thank you. So the first question is from Pranjal Pathak, and he says that if the universe is expanding, is only space expanding or the time is also expanding with it?
Well, time is ticking. Time is ticking exactly at the rate of 1 second per second, and we are guaranteed of it.
Okay. So next question is from Arjun Kanan, and he says that how exactly did the Event Horizon Telescope's virtual aperture span the entire diameter of the Earth?
So what we have is essentially measuring. There are 3 ways of looking at it. One I described. Imagine making if I can go back to one of my transparencies, which will illustrate this. Sorry for this. Okay. So let's look at the right side text, which is written in black. So imagine a big telescope of Earth size. So the question is, let me confirm again, because the question is about how a virtual telescope can be made of the Earth size, right?
No, sir. It's like, how exactly did the Event Horizon Telescope's virtual aperture span the entire diameter of the Earth?
That's what I'm saying. So this is, the telescope that was used for it is no different from what GMRT is and what this aperture synthesis telescope shown in this picture is. It's just that it was used for specific observation, which was very spectacular. The essential aim is to study something with that high angular resolution, which would come from instruments that will have to be of the size of the Earth, okay, to provide that resolution. After all, resolution depends on wavelength divided by the size of the aperture, effective size of the aperture. And so that could be done with this technique, which is called aperture synthesis, which measures similarity between signals, between pairs of antennas. And this measure of similarity between 2 locations is tied up with the distribution of intensity in the sky. through a Fourier transform. So there is a saying in Hindi, right? When the टेढ़ी उंगली से घी नहीं निकलता है तो I mean सीधे उंगली से घी नहीं निकलता है तो टेढ़ी करनी पड़ती है. So this is the टेढ़ी उंगली. When we cannot make a big telescope like this, we go to its Fourier domain and measure all the information in the Fourier domain that we can measure leisurely. Now, in principle, with just one pair of antenna and taking one measurement at a time and patiently moving the antennas to a different location and different spacing and orientation, we can make all measurements in certain plane called the UV plane, which is the spatial frequency plane. So one way of imagining is that the sky is made of whatever distribution it has, can be thought of as decomposable into set of sinusoids of different frequencies and different amplitudes and phases, which we are very familiar with in terms of description of any finite sequence of things. So we can imagine this is a superposition of a large number of sinusoids, sinusoidal patterns. And if we can make each one of them separately, which happens to be possible by measuring, taking one pair of antennas and measuring the similarity between the signals received. We can measure all Fourier components or all components or measurements of all sinusoids one by one. Now we can make this measurement with just one pair of antennas and it might take us forever. So somebody, they can take pity on us and say, okay, you know, I will give you n such antennas. And I'll say, great, I can now make n square such pairs and I can make n square simultaneous measurements, NC2 really speaking. And now this can speed up my measurement. So all that I'm doing is gathering pieces of information in one domain, which I know when Fourier transformed, when this information is collected, I can get the information that I want in the domain I desire, which is the image domain. Now, this is just like a hologram. Okay, if you're familiar with the property or description of holograms, we can actually have a hologram of the sky measured point by point. Okay, and we can also use Earth rotation as the additional dimension, because if two people are standing in east-west direction, the source at the horizon will see them not separated at all. But if as the source rises, it will see them separated by a different amount. And so in principle, the separation between two locations is as seen by the source. If the source sees it with different orientations, we will make measurements corresponding to those separations. And this can be exploited to use Earth rotation as additional help to realize ability to make different measurements without moving the two of us making the measurement. Okay, and many such pairs can make simultaneous measurements, and all of them put together can be collected and populated in a plane called UV plane, a matrix. And of course, there will be gaps. Not all measurements will be made. And so when we Fourier transform that set, we will get what is called the image made by such a virtual aperture instrument. Sorry, that's a long answer to a short question.
Yeah, it's fine, sir. Thanks a lot. Since I know there are a lot of questions that participants are asking, but we want to stick to our schedule as our next speaker is also waiting.
Yeah, so sorry for the delay in finishing my talk. I just want to say that they can, I can answer the questions later at convenient time.
Definitely, sir. So I request all the participants who are asking the questions that they can post their questions to the Slack channel that the link for which has already been sent yesterday, or you can email to Professor Adesh directly. So for next session, I would like to call Dr. Bindya Arora. Over to you, ma'am.
Okay. Thanks, Ishita, and thanks, Professor Adesh, for such a wonderful talk. Our next speaker for today is Professor Jasjeet Bagla, and he's an eminent professor. He's an eminent Indian researcher who has carved a niche for himself in the realm of astrophysics and cosmology. Having completed his master's from University of Delhi, Professor Bagla obtained his PhD from Ayuka, Pune in 1996 and later joined Harvard University as a postdoctoral fellow. After completing his postdoctorate, Professor Bagla got appointed as a faculty at HRI, where he served from 1999 to 2003. Currently, he is affiliated to ISER Mohali as the head of Department of Physical Sciences. His research interests include studying various aspects of cosmology. His recent work has been on gravitational clustering, cosmological n-body simulations, dark energy physics, and probes of high redshift universe. And today he is here with us to put some light on the gripping phenomena of gravitational lensing. Before he starts, I would request the participants who are connected through us through the YouTube channel to use the chat box to ask only relevant questions and do not spam the chat window, otherwise we miss some good questions. So thanks a lot, Professor Bagla, for being with us today. I invite you for your talk now.
Thank you, Bindya. Can you hear me?
Yes, we can hear you.
And can you see my the slides?
Yes, we can see that.
Okay, wonderful. So I'll get started. Thank you so much for the kind introduction. Just a small update. I am not the head of the department. I managed to get rid of that responsibility some time ago. So other than that, it's fine.
Right, thank you.
So I'll be talking about gravitational lensing and starting the story from a little bit before the first observation, which was made in May 29, 1919, giving you a little bit of historical background to that, and working our way slowly up to the Event Horizon Telescope observations, which led to the imaging of a black hole. And that entire idea of imaging rests very strongly on how gravitational lensing works in the vicinity of a black hole. So when did the idea of gravitational lensing come up? Well, first written mention is by Cavendish, but the first published version is by Soldner from Germany. He calculated deflection of light by a gravitational mass, and he did this in 1801. That's more than 200 years ago. And he exploited the fact that trajectories under gravitational influence are independent of mass. By that time, the speed of light was already known, not very accurately, but it was known. And he found that the deflection angle is given by 2gm by bc square, where b is the impact parameter, as you can see in the image below, and c is the speed of light, and phi is the deflection angle. So for a ray grazing the sun, the expected deflection angle is about 0.87 arc seconds, which is very, very tiny. So the moon, for example, is 30 arc minutes, and you know that 1 arc minute has 60 arc seconds. So we are talking about roughly an angle which is 1 divided by 2,000ths the size of the moon on the sky. So this is something which was published in 1801. And then much, much later, 1911, Einstein arrived at exactly the same result by using the equivalence principle. So as you are aware, equivalence principle essentially says that if we are in a closed room, small room, then it is impossible for us to say whether we are sitting in a gravitational field, uniform gravitational field, or whether we are accelerating with uniform acceleration. So in both the cases, for example, if I drop a ball, it will fall down and its acceleration will be exactly the same, its trajectory would be exactly the same. So Einstein argued on the same grounds that if I now have a tiny hole in the side of the chamber and a light ray comes in horizontally into this, because of acceleration of the rocket, the light ray will be seen to bend, and therefore the same thing should happen in a gravitational field, and we should see bending of light. He arrived at exactly the same formula that Soldner had used. He published this in 1911, and he was very excited about it. So he wrote to a large number of people requesting them that, look, can somehow this thing be measured? And of course, all the observers told him that it can be measured, but it can be measured only during a total solar eclipse, not otherwise. So there was an eclipse coming up in 1912. So some of the astronomers set up expeditions. Their idea was to essentially study solar corona and take pictures of the eclipse. But Einstein's claim also enthused some of them, so they wanted to see if deflection of light can be measured. So in 1912, the Argentinian expedition to Brazil failed to observe anything due to very poor weather. There was a German expedition to Crimea, as was an American expedition to Crimea. They were both caught up in the First World War. In fact, all of their equipment was confiscated. The Germans, being an enemy nation in the war, all the German astronomers were jailed. And one of them, whom Einstein had persuaded to go, Einstein had to use all of his influence in Germany to get him released in the first exchange of prisoners. He came out, other astronomers from US and so on were allowed to leave, but the equipments remained there till 1919, 1920. Now, Einstein, of course, kept on working on his theory of gravity, and he completed his general theory of relativity in 1915. And once this was done, he realized that in this theory, the bending angle changes, and it is about a factor of 2. In fact, exactly a factor of 2 larger than what had been calculated earlier by Soldner and by himself. So he wrote papers about this, but by now the First World War was in full swing, and therefore there was very little communication going on between warring nations, and any information which went from one country to another had to be through neutral countries. So the main reason why there is this factor of 2 coming up is that the equivalence principle calculation is purely kinematic, and the Newtonian calculation does not account for the zero rest mass of photons. So when all of this is taken into account, I cannot present that calculation here. It is somewhat lengthy and also tedious. The deflection in the weak field limit turns out to be 4 gm by bc square instead of 2 gm by bc square because of these additional factors. So Eddington during the First World War was the Plumian professor. He had been the Plumian professor since 1912. This is the most prestigious astronomy chair in Britain. In 1914, he also became the director of Cambridge Observatories, and he had been a part of the 1912 expedition to Brazil. It is important to appreciate Eddington's background as an observer as well as a mathematician. He Eddington was one of the few people who completed the tripos in mathematics at Cambridge in record time, and also with record scores. He, as an observer, worked in Greenwich observatories and then later on in Cambridge observatories, where he improvised the methods used for uh, trying to measure the measure distances to stars using parallax. Now, as you are aware, the nearest star to Earth is more than 1 parsec away, more than 3.5 light years away. And as a result, the parallax shift in their position is less than 1 arcsecond over the entire year. So Eddington was used to measuring angular shifts, which were very, very small. And he also had mathematics training. So he learned about the relativity, first about the relativistic prediction, and then he read up on the relativity theory because he was able to get Einstein's papers from De Sitter, who was sitting in Leiden in Holland, which was a neutral country at that time. So within the Royal Astronomical Society setup, he emphasized the need to test the theory of relativity. And he understood the fundamental problems which had arisen with Newtonian mechanics and Newtonian gravitation theory once Einstein's special relativity is taken seriously. he realized that action at a distance was no longer a viable model. Once you know that there is a speed of light, uh, that the speed of light is the maximum speed with which signals can propagate in the universe. So he was looking for alternatives, and he felt that general theory of relativity satisfied those criteria, and therefore its predictions need to be looked at very seriously and tested as much as possible. So he was in some sense a unique astronomer at that time. Not many astronomers had the mathematical background to understand relativity, and also not many astronomers had the wherewithal or the training to measure angles or shifts in angles which were of the order of less than an arc second or of the order of 1 arc second. The other person, as I said, De Sitter played a very important role. He was a mathematician, physicist, and astronomer. He gave one of the earliest cosmological solutions to the theory of relativity. And his solution, of course, depressed Einstein a lot, because Einstein had thought that he had achieved discovery of a Machian theory in discovering the theory of relativity. But if De Sitter could give a solution without any matter, then clearly something was wrong. So De Sitter was at Leiden during World War I, and he was able to communicate both with people in England and with astronomers, the physicists and astronomers in Germany. The astronomer royal at that time in UK was Frank Watson Dyson, and he had been a mentor to Eddington in terms of astronomy, and it was Dyson who had developed techniques for measuring positions of stars from photographic plates, and then essentially refining techniques so that small shifts could be measured. He, as Astronomer Royal, was the chair of something called a Permanent Committee of the Royal Society and the Royal Astronomical Society for eclipses. He realized that the eclipse of May 29, 1919 was particularly useful for measuring the reflection of light. One reason is that the sun would just be north of Hyades cluster. This is an open cluster of stars which you can see in the sky in winter. It has a number of relatively bright stars. None of them are very, very bright. But if you take a random region in the sky, compared to that, there are several stars close together, which means that you can measure the deflection. And you can possibly even measure the dependency on the impact parameter B, because different stars will be at different impact parameter, and therefore their angle of deflection would be different. And the other reason why he realized that it's an important eclipse is that it's one of the longest eclipses, total solar eclipses on record. So you have enough time to take pictures. It was decided to put together two expeditions, one to the island of Principe off the West African coast and another to Sobral in northern Brazil. The proposed budget was £1,100, £1,000 for travel and £100 for instruments. So this is the note which they had, where they asked for this particular grant from Royal Society, and the money was given. And they were lucky that the war was kind of ending, so they were able to put together a small team. But they did have difficulties, because if you look at the lower snip, which are the text which I have posted here. In November 1918, the only workman available at the Royal Observatory was the mechanic, the carpenter not having been released from military service. In these circumstances, Mr. Bowen, the civil engineer, was consulted. He kindly undertook construction of frame huts with canvas, which could be easily packed and readily put together. So they had to do a lot of jugaad in order to put everything together. And two teams set sail sometime in March. So this is the map of where all the total eclipse could be seen. The red line is the central part, and totality could be seen in the blue band surrounding that. So you can see that on the western side, Brazil has a lot of territory where total solar eclipse could be seen. Then somewhere over here, you have the path touching Liberia. and then it goes into Congo and Tanzania and so on. So zooming in on the African part, so they had two choices. One was Liberia, the other was an island over here. The third site they considered was Tanzania, but they felt that in Tanzania, the elevation of the sun will be very low and that can cause problems. They looked at the weather records, which turned out were completely wrong. So they decided to go to Principe instead of Liberia. In the event, it turned out that Liberia had very clear skies, but no one with the equipment. Principe had a thunderstorm, which cleared for a brief while so that Eddington was able to take some pictures. But when Eddington arrived in Principe, all the locals kind of laughed at him when he said that he expects to observe an eclipse in the month of May because that is their rainy season. So this is zooming in. This is the island of, so these are the two islands. This is Principe, where Eddington had gone. This is the other part of the track in Brazil. And you can see Sobral is over here. So this is in a reasonably high altitude area, and one has to go up along the Amazon and then on other tracks. So because Dyson was a royal astronomer, he could not go. Eddington was forced to go because of his problems with the draft and his comments which he made about against the war. So essentially, the government was told that going for an eclipse expedition will be equivalent to military work for Eddington. The other team was led by Andrew Cromlin. He was from the Greenwich Observatory, and they had clear skies, but they had other problems which plagued their data. So this is a picture of the setup at Sobral. So these are the tents which that naval engineer built for them. These are the two telescopes. This is the main telescope, but one of the members of the eclipse committee, Father Koti, he insisted that these people take the other smaller telescope with them. Telescopes were fixed in a horizontal position, and these mirrors were moved so that sun always shone into the telescope. And this is where the results were published. You will notice that the first author is Dyson, then Eddington, and then Davidson. And Cromlin, who had led one of the expedition, is not mentioned. Father Koti, who had a lot of experience in observing eclipses, could not be spared as schools were opening up after the war, and he was needed to run his particular school. So this is where the sun was expected to be. This is actually one of the plates taken by by Eddington. You can see the corona over here, and locations of different stars are marked over here. So these were the stars for which they wanted to measure the position and compare with the positions of same stars when the sun is not there. So these two stars over here are the two stars over here. They're nearest to the sun, and yet the impact parameter was different enough so that one hoped that one can see the variation of deflection angle with the impact parameter. So this is the Hyades cluster, and this is the bright star in Taurus. Many of you would have seen Pleiades, Kritika in the sky. So they actually mounted the telescope so that they could get a large number of stars in the frame. So this square is what would have been if they had just kept the plate horizontally, but you can see that the telescope is mounted in this strange diagonal kind of a position, and that was done to maximize the number of stars within the frame. So in the event, it turned out that the main telescope at Sobral malfunctioned. There were issues with rapid change in temperature, which happens at the time of eclipse, and therefore they felt that the plates were somewhat distorted. Data from the 4-inch, which Father Corti had insisted they take along, turned out to be superb. Eddington had very few observations because the sky was cloudy except for a few minutes, and he got some data, but not a whole lot. Data from Sobral was analyzed in the Greenwich Observatory. Data which Eddington collected was analyzed by him. All of this was then put together. So amongst the sites, as I mentioned, Liberia was dropped because of likelihood of poor weather. Tanganyika Lake was dropped because of low altitude of the sun. Team at Sobral had problems with the main telescope. They tried to mask it, but in the end, they ran into problems with that. And the idea was to stay on at least up to end of July and get pictures of the same part of the sky without the sun in it. And the team at Sobral did do that. Eddington could not stay back because sailors were going to go on a strike. So within a day or so of the eclipse, he had to pack his bags and leave. So these were the results. The results were from whatever Eddington could measure at Principe and the 4-inch telescope at Sobral. So this is the upper line, straight line. So black line is their best fit. The points are the different data points coming from different stars. The dashed line is the Newtonian or equivalence principle prediction, and the black solid line is the Einstein prediction. So they made a measurement which seemed to be consistent with Einstein's prediction, and so it remained, and error bars were considered too high. So within the scientific circle, although they could claim that they have ruled out the Newtonian calculation and the equivalence principle calculation, but it was not taken very seriously. Australian astronomers did a very good job for the 1922 eclipse. Actually, the American astronomers in Australia, they did a wonderful job at that time. American astronomers could not observe the 1919 eclipse because their telescope was stuck in Crimea, and it reached back only after the eclipse was over. So it's in the measurements were made on May 29, and the data was analyzed by September. It was sometime in November that they finally made a formal announcement. And that measurement and the announcement made Einstein an instant celebrity. And this happened even though measurements were thought to have large errors and were not accepted within the scientific community immediately. It took some time, particularly till Campbell's observations of 1922 eclipse came along, that this particular measurement was taken as confirmed. However, general theory of relativity became an accepted theory after the measurements, and a lot of people started working on it. Over here, you can see Einstein in conversation with Eddington in the garden of the observatory at Cambridge. You can see the observatory building at the back. There is a room inside that, which used to be Eddington's room for receiving visitors. With the space crunch nowadays, that is a seminar room slash dining hall for students and postdocs, and a lot of informal discussions and seminars happen over there. Many measurements have been made, not only in the optical for the sun, but with a large number of different instruments, including in radio. And this is a chart of all of these measurements. You can see that the VLBI measurements are particularly precise, and they put very, very strong constraints. So here it is plotted as 1 plus gamma by 2. This is a way of representing all relativistic theories, not just general theory of relativity. And in general theory of relativity, gamma is 1. So because gamma is 1 in this theory, but it can take different values in other theories, this means that most other theories are ruled out from such measurements. So how much the things have progressed. This is a paper published in Classical and Quantum Gravity in 2018. And these were the starlight deflection measurements made during the 2017 solar eclipse by an amateur astronomer. You can see his picture in the middle panel over here. And this is the 1 by B curve that he fitted using his data. So in about 100 years, the whole thing has become, the technology has developed so much that even amateur astronomers can make these measurements. Now coming to gravitational lensing at larger scales, what you see over here is a picture of a cluster of galaxies, Abell 1689. It's a picture taken by Hubble Space Telescope. Credits are given on the right. You can see yellowish galaxies, most of which are in the cluster. You can see a few stars which appear with a cross. But you also see a number of bluish images which are arcs, like this one over here, this one over here, and then there is an arc running across over here. These arcs seem to circle the cluster of galaxies, and these are actually images of a single galaxy in the background. So this is the kind of framework that we have in mind, that we are observing from the vicinity of the Earth. The galaxy we are seeing is very, very far away, and there is a large mass concentration somewhere in between, which bends the light rays and causes us to see multiple images of a source which is in the background. And these multiple images are seen around the intervening massive object. Now, one theoretical simplification which is done in trying to understand gravitational lensing is to say that I have only one major deflector. The other is that the distances between the observer and the lens and the source and the lens are both very large as compared to the size of the massive object which we are dealing with. So we can think of it as a single deflection. It's almost if I had some strange kind of an optical lens, thin lens somewhere in between the source and the observer, and that is causing all of the deflection. Then I can think of light on both sides of the lens as traveling in straight lines in the geometric optics limit and suffering only one deflection. And that deflection angle I know from Einstein's theory in the weak field limit is 4 gm by bc square, b being the impact parameter, except that unlike the case of deflection by the sun, here there is a mass distribution extending all over. Some light rays may pass over here, some light rays may pass over here. So each will get deflected by the amount of mass that is contained inside the trajectory. Okay, so one thinks of a source plane and an image plane and the observer. If we think of light rays as starting from the source plane and then appearing in the image plane as seen by us, then it is a mapping from a small plane at the location of the source to another plane at the location of the lens. But this mapping is not one-to-one, it can be one-to-many, particularly in the regime of strong lensing. Of course, I can have a source plane at different distances from the lens, and each one of them will have their own characteristics. So what I will do now, instead of trying to dwell on theory or mathematical formulae, is to show you some videos of what happens if I have a gravitational lens, I'm observing, and I have a galaxy kind of magically sliding across in the source plane. So this will give you an idea of what happens for different source locations in the source plane and what kind of images we see. Yeah. So that, though I will show you that in a moment, but let me give you the history of gravitational lensing. So Einstein had done his calculations in detail, but he had never written a paper. He was forced by his colleagues to write a paper which he finally published in 1936. And in 1937, Swiss astronomer Fritz Zwicky, he suggested that galaxies and clusters of galaxies may be able to cause detectable gravitational lensing. This was not observed for a very, very long time, and first observations happened in 1979, where multiple images of a quasar were observed. So on the right is an image of this particular region. You see a very bright source in the middle. If you try to look carefully, and you can go look at the image using the link which I have given over here, you will actually see two quasars sitting over here, or 2 point sources sitting over here. So in 1978, these quasars were discovered by a team of British and Australian astronomers, and they thought that it's strange that they have two almost identical looking quasars so close to each other, because such bright quasars are typically found far away from each other on the sky. Then they took spectra, and they were astonished that both the quasars were at the same redshift. It was only then that it kind of dawned on them that maybe it is the same quasar, and we are seeing two images of that quasar. So here is this animation. On the left, you have the source plane, galaxy is moving in. On the right, you have the image plane. And you can see that as the galaxy moves in, it gets multiply imaged. There's almost a ring, now a quadrupole, again a strange kind of an arc. And then we go back to a single image. I will run this animation again. So you will notice that we go from a single image for the source galaxy, to 3 images, to 5 images, then back to 3 and back to 1. The other thing to notice is that even when there is a single image, the image is distorted. It is forming a kind of an arc around the center. You can see pairs of images being born or pairs of images being annihilated. Let's do it one more time. So notice that it's always pairs of images which form together. They form either around this curve or around this curve. These lines are called critical lines in the lens plane. The other is that the images are always tangential. They are arc-like around the cluster, around the lens. So I'll have formation of a pair around the green line here. Here, you can see that happening. And now around the red line, red critical curve. As the galaxy move out of the inner caustic, you will see annihilation of a pair of images there, and annihilation of another pair of images there. All of this can be understood in terms of catastrophe theory. I do not wish to go into those details over here, but using catastrophe theory and classification of images, one can discover very interesting kind of image formations. So let me show you one other. you can see that the image is kind of going around a little bit. Now, in this one, you will see formation of 4 images together. And the interesting thing is that they form some kind of a ring, distorted ring, but this distorted ring is not centered around the center of the cluster, but it is off center. You can compare with the previous image. These images form some kind of a ring over here, but that ring is very large. It is almost the size of the lensing object. This kind of a ring, partial ring. Okay. This is centered at the deflector and it is of the same size as the deflecting mass distribution. But in the next one, we will see that the ring which forms is very small in size and it is off center from the reflector. Here. So such peculiar points can be found using the mathematical structure of gravitational lensing. I'll show you one more type of a point which does not form a ring or an arc at all. It has a very strange kind of an image structure. I should add that this slight small offset ring which I have shown you, one example of this kind has been seen in real life. But the next one which I am going to show you, nothing of that kind have been seen. And the basic reason for our studies right now is that observations are likely to increase the number of known galaxy clusters by a factor of 20 to 50 in the next 10 years. And we are hoping that these rare image types will also get discovered. So along with my student Ashish Meena, who made these animations as well, we are looking at exotic image formations which may get discovered and which can then be used to say something about the mass distribution of these deflectors. Again, you will see that always pairs form and pairs annihilate. Approaching the singularity from a slightly different direction. So you can see that gravitational lensing, even in the weak field limit, can lead to very exotic image forms. And all of this variety is in fact for just a single deflector. If you had more, then the variety can be even more in principle. Now, all of you would have seen this particular image from, it was released in March last year, Event Horizon Telescope, black hole at the center of M87. So one would like to, Desh has already spoken a little bit about how radio astronomy is used to achieve this super resolution, building an effective telescope with an effective aperture almost the size of Earth. But what is the physics that we exploit in order to say from this image that there is indeed a black hole at the center of M87? And that is basically related to how gravitational lensing works in the extremely strong regime around in the vicinity of a black hole. So we have seen that deflection for in the weak field limit is very small. For the sun, it is of the order of 1.7 arc seconds. But if I go close to a black hole, the deflection can be strong. I can have a sharp U-turn of light rays. And if I try to go closer, if I try to decrease the impact parameter, I can even have photons doing a loop, full loop, and then almost going back in the same direction, doing 2 loops, or doing even 3 loops. But you will notice that no matter what I do, where the photon comes in from, I never go. So this is the outgoing direction, let us say. This is the center. The gap between these two is never smaller than some number. So the whole idea of Event Horizon Telescope was to look for this dark patch in the middle. Now you might ask why this ring is not uniform. It is bright in one side, dark in the other. That is caused by the fact that in this particular case, there is a lot of matter which is orbiting the black hole in its vicinity. It's called an accretion disk, and that accretion disk is very hot, and material in that is orbiting at speeds almost at the speed of light. Because of that, there are special relativistic effects which cause the emission from this moving material to go in one direction and not the other. And that is what causes one side of this particular image to be much brighter than the other. So this is the other very extreme regime. Of course, gravitational lensing can give you very subtle distortions, which are not easy to see. That regime is called weak lensing, and that is being used by astronomers all over the world to try and understand the mass distribution of distant objects on the sky. That is an effort which has now been going on for more than 2 decades, but it is likely that it will take some more time before we can say things with certainty, because the errors, systematic errors in that analysis are very high. So this is my summary. Gravitational lensing has now been known for more than 101 years. Lensing has been used to estimate masses of objects that cause gravitational lensing, confirming the presence of dark matter in galaxies and clusters of galaxies. And aspects of lensing in the extreme regime in close proximity to black holes have been used to image a supermassive black hole in M87. So I put image in quotes because you are actually not seeing the black hole. You are seeing a hole created by deflection of light by the black hole. So it is an image, but not quite an image. One topic which I did not touch upon, because that takes us in a very different direction, although it's very, very exciting, is that lensing of gravitational waves can show signatures of the wave nature in lensing, as we observe gravitational waves with wavelengths of millions of kilometers. So think of a situation where I have waves in on water surface in a pond. If I have a stone or a blade of grass in the middle of all of this, and there are waves which are cruising, if the wavelength is small, then this obstruction can cause a deflection. But if the wavelength is much larger than the size of the obstruction, it simply doesn't matter. And it's in the transition regime between no effect and going towards almost the geometric optics limit that some interesting things can be seen. And we have been working on that as well. So I thought I'll at least mention that, because that can give you some very interesting insight into phenomena related with gravitational waves as well as lensing. So I will stop here and take questions. Thank you.
Okay, so thank you so much, Professor Bagla, for this informative session on gravitational lensing, starting from the historical advances to the present day scenario. Undoubtedly, gravitational lensing is currently a booming phenomena in the field of astrophysics. And as expected, we got a couple of questions for you from the audience. So may I proceed with the questions?
Please.
Okay. So the first question is by Mr. Ashwin. He is asking that is lensing of waves possible even in other wavelengths except for the optical ones?
Yes, it has been seen in radio wavelengths, in X-rays, and so on. So it's a phenomena which is completely independent. It is an achromatic phenomena. The phenomena is independent of wavelength, and it has been seen in many, many different wave bands.
Okay, thank you, sir. And the second question is by Mr. Abhishek. He asked it, how does mass or energy interact with the space and bend it?
Uh, okay, so there are two aspects to it. One is that whenever you have mass or energy at any given place, then that causes the space-time curvature in the vicinity to change. For example, the sun changes the space-time structure in its vicinity, and therefore anything which is moving in the vicinity of the sun senses that modification in space-time structure, and their trajectories get modified. At the crudest level, for massive particles, Newtonian approximation is a good one, although we know that for even things like Mercury, we can see deviations from Newtonian theory if we observe long enough. So this is so there is an effect of mass and energy on space-time curvature, and then space-time curvature tells test particles or particles in the vicinity as to how to move, if I can put it in this way. I hope the answer is clear.
Okay, thank you, sir. And the third question that is by Anush Krishna. He has asked it, why only gravity can bend space-time and the other three forces cannot?
Well, the other forces which we have cannot be absorbed in the description of space-time, for the simple reason that the charge for gravity, which is the mass, is the same as the inertia, which is also the mass. So inertial mass and gravitational charge, they are proportional to each other, and we work with the units where they are identical. We cannot do that for example, electrostatic charges. Over there, the amount of charge which any particle carries has nothing to do with its mass. And we see this time and again in electromagnetic theory, where the E by M ratio plays a very important role. In case of gravity, M and M cancel. And therefore, whatever happens can be described in terms of pseudo forces and absorbed in the description of space-time. Whereas for other forces, this kind of a description is not possible, simply because they have a charge which is completely independent of mass, and therefore both charge and mass play an important role in how things behave. So if I have a single electron or a single proton, I apply the same electrostatic force, they will behave differently because they have different E by M ratios. But if I have a given gravitational field, no matter what object I take, it is going to move in exactly the same way if I give it the same initial conditions. So whether I put a electron into a gravitational orbit around Earth or a proton into gravitational orbit around Earth, their trajectories will be identical, irrespective of their charge. But if I had an electrostatic field, then to the same electrostatic field, they will respond differently because they have a different E by M ratio.
Okay, thank you so much, sir. There are still a number of interesting questions left in the chat window, but as we need to abide by the time constraints, we cannot take all the questions. However, I request the audience to always contact Professor Bagla regarding their queries. And yes, you can also post your questions on the Slack channel, the link for which has already been shared. With this, I again thank Professor Bagla for treating us with this wonderful session. Over
Thank
to
you,
you,
Bindya.
Dr. Bindya.
Yeah, thanks a lot, Professor Bagla. Thanks a lot. And thank you for wonderful animations. I mean, even I could understand most of the stuff. So thanks a lot.
Okay, I'm
Uh,
glad. Yeah.
and we now have Professor R.C. Singh and Professor N.P.S. Saini, who have been with us throughout the start of the session. And I've always appreciated their support they have given to me. I request Professor R.C. Singh to kindly share a few lines of motivation for the kids. Professor Singh, yeah, okay.
Yeah, I'm still on.
No, you're audible, but your volume is very low.
I'm still on
Yes.
that data. I don't know whether it's yeah.
Okay.
So Is it audible now?
Yes, sir.
Hello,
Yes, sir.
is it audible? Okay. So I highly appreciate Rishabh, Simran, Ishita. So I'm very thankful to all the team because they have arranged so many speakers, especially Avinash Deshpande, Jasjit Bagla, and this field, they are very much connected to this field, and I hope while listening these interesting talks, they will be, interested in further research or, I mean, professionally somewhere, either in India or some abroad. And I hope this will be very beneficial, or it's a motivation for them to choose their field of interest. And I again thank you all the speakers, and I also I appreciate that I appreciate and I encourage the coming speakers in the next session also. So
Thank you, Professor Singh. Now I request Professor Saini to kindly share a few words.
Hello, am I audible?
Yes, sir.
Okay. First of all, many congratulations to Bindia and her team for organizing such a wonderful event, right? So this credit mainly goes to the members of the physics club, especially Ishita, Abhijit, Simranpreet, Rishabh, who from the they all are working in this club for the last many years and focusing very, you can say, the deep aspect of the science in different areas, right? Okay, and I think they are with us for the last 5 years and doing many small, bigger event to starting from the small school classes to the college and university level. Okay, this event is also very interesting. Okay, for I think everyone enjoyed a lot. Also, they have listened to the two speakers about the different aspects of astronomy in different ways, whether they are gravitational waves or radio waves or different. There are so many waves are there. Okay. I must appreciate efforts by, especially by Bindia. She is basically not only mentor, okay, she is a very big force from the physics department behind the students for organizing such events, okay. I wish that these kind of events should also be arranged in near future also, so that you can connect more students from different areas. You know, this time I mean, looking at the program, so most of the students are from Delhi area, okay, those who are going to present their papers and oral talks, okay. I hope in next program, students from our university, they must also participate, okay, in this, okay. So finally, I also thank to the speakers, especially I know Jasjeet, but I listened to Dr. Avinash first time. Both have given very wonderful talks here. Okay, so I hope students have enjoyed these talks. Okay, and they have learned many new things. And for future, I wish you all the best to arrange such kind of event. Thank you very much.
Thank you, Professor Saini. Thanks a lot. So we'll have a 10 minutes break now, and we'll rejoin at 12:30. So we are going to keep the Zoom windows on and not log out. Thanks a lot.
Good afternoon, everyone. So we are ready for the first session of our oral presentations. So very warm welcome to everyone in this session. We have a total of 5 talks in this session. So the first talk is by Rashmi. She is doing her BSc Physics honors from University of Delhi. So she is going to present her talk about optical telescopes. So I will invite Rashmi to start the talk, please.
Hello, am I audible?
Yes, you are audible.
Okay. Good afternoon, everyone. I'm Rashmi, and I will be speaking on optical telescope. So let's start by who. Let's start by who invented the first telescope. Now, binoculars have been used by sailors since, right? And then one day, Hans Lippershey, an optician, he was working in his lab, and he suddenly realizes that if we use lenses with a certain distance apart, you can see the objects very clearly. So you can see the objects very clearly, and that's when he realized, and then that there's a use of lenses which is more the first guy to scopes, but they were usually for terrestrial viewing only. Nobody really knew, like, and that's when to see. To see the celestial bodies in the night sky. He used to see the faces of the moon, and he used to make these very popular among the masses where he used to live, and that's how he became the father of observational astronomy. Now, these telescopes, which use lenses, are known as refracted telescopes. They simply use 2 lenses, and one of them is the primary lens. The other one is the eyepiece, where we see the image, and we will be seeing how they are worked in just a while. So, what was the purpose of the telescope after the telescope pointed into the sky? The purpose of the telescope, the most important purpose, is to collect the light. So, to understand what a telescope does is to imagine them as light collecting buckets. Let's take an example where we have a telescope with a small diameter, and the other telescope has a bit bigger diameter, has a bit longer diameter. So in the first telescope, when you are seeing a source, you cannot see the fainter details. But as soon as you increase the diameter of the lens or the telescope, you will start noticing very faint details, which were known as sensitivity, and the light collecting area directly depends on the square of the diameter. So even a simple increase will give you very drastic changes. Now, other than the sensitivity, we also have resolution. So just as the diameter of the lens increases the sensitivity, it also increases the resolution. So in first case, we can see that we have a point source, and we cannot really see that whether it's a point source or is it a binary star system or something like that. But as soon as we take an example where we increase the diameter of the telescope, so the resolution power becomes in such a way that it can resolve even finer details. So what was a very fine, what was a point source before is now resolved as a 2 system. Like there are 2 light sources, not just one. So that is the second use of telescope to see structures which were very opaque to us. And that you can also notice is, like when you see in the night sky, you will see just stars. It's actually binary star system or triple star system. So that's use of telescope is to magnify things. Now, telescopes are not generally used to magnify things, but it's just a feature how they are arranged. So this is an example of refracted telescope. lens, this is the eyepiece, and this is the focal length of the objective. The image is formed here, and then the resultant image is formed here, which is magnified. So magnification is just this focal length over this focal length. And we see magnified objects when we see through a telescope, but the purpose is just mainly to resolve things and see more fainter detail. Now, these lenses have a very big issue with them, which is chromatic aberration. Now, when we use lenses, and a simple way to understand the chromatic aberration is when you use a prism, it reflects the lights in several colors depending on the wavelength. So there is blue light and then there is red light. So the focus point of both of these lights are different. And if you see something, let's say, suppose you are observing Saturn, so you will see something like this when you look through a telescope. So this is not really a good image to see. So how chromatic aberration is fixed is using two lenses. As soon as you use two lenses or more than two lenses, you can fix out the different focal points. That's how the lenses are converging the image. And then you can see this image of Saturn as a result. So chromatic aberration can be cured, but even though we cure it, we can still see that there is something left, like there's not just, proper, it cannot be corrected to the very fine details. Now let's example of video which uses 40 inches wide lens here. Now, but this observatory is not used anymore. This has a lot of telescope, but don't you? Problem with telescopes, as I was talking about, is the first one obviously being the lenses are very expensive to build as you make bigger and bigger lenses. And they also have glass impurities, like you cannot, just get rid of glass impurities. So
Rashmi, there was some internet issues, I think, and the screen shared has stopped. So can you do that again? And also, you have just 1 minute left of your full time. So yeah, keep it in that.
So I was lenses is very expensive. They have glass impurities, and they are very bulky when you pick them up in big. So what we came up with, not use lenses, but use mirror reflex telescope. Use mirror. So mirror comes in bends, and there is no chromatic aberration seen in a case of reflecting telescopes. A simple works is there are two mirrors. One is plane, and the other one is either concave or parabolic. And then you have the eyepiece, a lens through which and in the talk about how you should choose your first telescope. Now you saw that there are many things refracting telescopes suffer from, so you can just simply choose a reflecting telescope. But even after choosing the reflecting telescopes, you have an option to choose which mount. So there are two types of mounts. The first one is alt-S, which is simply altitude and azimuth. It means you can move the telescope up and down, left and right in whichever direction you want. And the second one is the equatorial mount. And one of the points is situated at the Polaris. So it is fixed at the Polaris. And as soon as the night passes, you have to move it along just one axis. So you don't have to move it along two axes. So if you are a beginner, you can choose the alt-S. And if you are someone who wants to do astrophotography or more research-based astronomy, you should go for the equatorial mount and that kinds of telescope. So I would like to end my talk here, and if you guys have any more questions, you can ask in the comments.
Thank you, Rashmi. It was really an amazing talk. So I have one question for you. We know that the optical space telescopes, such as the Hubble Space Telescope, they take pictures in black and white. So my question is, why do they take the pictures in black and white? And on what principles are the colors added later? So what is the crux of adding the colors? What is the basic formula that they use for adding the colors later?
Okay, so as you had Hubble Space Telescope or any other space telescope for that matter, they use black and white images. And when they take the images, they note down at what frequency they are observing, from the Vipure, from violet to red, yellow, green. They observe all the colors. And after taking the image, they see like which wavelength and this is the yellow, green colors, after seeing which wavelength they were present at when the data was collected. So to make them visible, how they would appear to the human eye, to the visible light. That's why they observe in not just optical, sometimes they observe in infrared too. So that's why they have wavelength, so they cannot add just color right at the moment. They make the pictures infrared and other wavelengths like that, and they add colors according to the human eye. So that pictures are made so that we can recognize them.
Okay, thank you so much. Over to you, Shankar.
Thank you, Rishabh, and thank you, Rashmi, for the talk. So before inviting the next speaker for the talk, I have some points or like some guidelines so that all the speakers must adhere to them. So the first one would be, please keep your talk in the time limit. So the time limit is between 6 to 8 minutes. So try not to talk more than 8 minutes so that we can remain on schedule. And the second thing that I would like to suggest is that if you have a weak internet connection, please stop your video so that we can hear you and see your slides properly. So now I'm going to invite Rishabh Jain. He is doing his BSc Physics Honors from Crorimal College, University of Delhi. And he's going to talk on adaptive optics. So Rishabh, you can start sharing the screen.
Hello, am I audible?
Yes, you are audible. Please go forward.
Thanks a lot. Okay, so thank you, Rashmi, for your wonderful talk about the optical telescopes. So now I would like to talk about adaptive optics, the art of shaping light. My screen is visible or not?
Yes, it is visible. So you can start the slideshow.
Yeah, okay. Yeah, so I would like to start with this diagram showing variation of atmospheric opacity with the wavelength. Here we can see that there is a huge gap in the radio wave band and there is a small window in the optical wavelength. So when we try to look out of the Earth through large telescopes, the atmosphere that is our friend becomes our enemy. Causes, here's what, here are the limitations that are imposed by the Earth's atmosphere, that are opacity, the wavelengths are absorbed at different wavelengths, and also they produce local thermal radiation. The loss of luminosity and the turbulence is caused by the atmosphere. And we know that the image is formed in the optical telescope and the angular resolution is given by theta is equals to lambda by d, where lambda is the wavelength in which we are observing, which is generally optical or infrared, and d is the diameter. And here we get a peak intensity, right? But what in the case of turbulence? Suppose a wave, we are getting waves from a distance source, and here is the turbulence. So the wavefront that was earlier straight gets distorted, and we don't get a focused image. Instead of getting a peak, we get spreaded function. And the theoretical value that we were expecting of angular resolution was lambda by d. That was diffraction limited image. Instead of that, we are seeing limited image, which is given by lambda by r naught, where r naught is the Fried's parameter. So you can see that this is what we are expecting theoretically, and this is what we are getting due to turbulence caused by the atmosphere. The peak gets spreaded. Now, what's the solution? Adaptive optics. It can undo all these effects and provide us a diffraction limited image. Now here's a video showing how adaptive optic system works. A sodium beam is fired, a very high energy sodium beam is fired up to the atmosphere. It strikes the ionosphere and excites the sodium atoms. And we make an artificial star. And then we measure the light coming from it. This is known as laser guided star. And now we'll be measuring the light coming from it. And through that laser guided star, we'll be getting how much distortion this atmosphere is causing at a particular place. So this is how an adaptive optic system works. All right, so this is the waves from that laser guided star, and we can see here the distorted wavefronts are coming. This image here formed is turbulent. The wavefronts coming from the star are not proper in the shape. They are distorted, and then these distortions are carried forward, and here is a deformable mirror that changes its shape in the form of distorted wavefronts, and it corrects the wavefront, and we get corrected wavefront. We again get a sharp image with a peak. Here we get the sharp image again. All right. So here are these wave fronts coming from the atmosphere. This is a deformable mirror which can move very fast and change its shape according to these distortions. And then the corrected wave fronts go out. And we get back the peak intensity. You can see the difference that if we don't apply the adaptive optics to an image of a star, it looks spreaded. The wave function is spreaded. But if we put the AO on, we get the peak again. And here's what an adaptive optic system looks like. This is Subaru telescope, 8-meter telescope located at Hawaii. And this is the size comparison that how large is an AO system looks like. And these are some original images from Subaru Observatory. These are components of AO systems. And we can see here some results of AO. This is an image without adaptive optics of Neptune without infrared and captured using Keck Observatory at Mauna Kea, Hawaii. So, these sodium lasers are being thrown out to the atmosphere, and with the adaptive optics we can see that we can get a much clearer image. And there is an image of Saturn and Uranus with the help of adaptive optics taken using Keck. And this is the galactic center. You can see how clear image we can get through adaptive optics system. Here's another image. And there's TMT, the next largest telescope project being built at Mauna Kea at Hawaii. So this telescope has a diameter of about 30 meters. In can see the size comparison. Hale telescope is about 5 meters. Hubble is about 2.5 meters. Keck is 10-meter telescope, and this will be 30-meter telescope. And India is contributing a lot to 30-meter telescope, and it will be using adaptive optic system to give a clearer image of the universe. And these are some references and some books that I used for adaptive optics. So now I would like to end my presentation. Any doubts and questions are most welcome.
Thank you, Rishabh. That was really very insightful talk. So we have one question from Kumi Das. She's asking, how is the distorted wavefront resorted into shape wavefront, its mechanism?
Yeah. So let me get back to the slide here. So these are distorted wavefronts coming from the atmosphere, and they strike the deformable mirror. First, we measured how much distortion is caused by the laser guided system, and then these deformable mirror change their shape in the direction opposite to the distortion, so that they give us the corrected wavefronts.
Okay. And we have another question that was posed to the previous speaker, but since it was posed at the end of the presentation, we could not ask. So I think you can answer that question since you have a good knowledge of telescopes since we last met. So the question is that what is the difference between Cassegrain and Dobsonian telescopes?
Yeah, so Dobsonian telescope is basically a type of Newtonian telescope with larger focal length, and it has a long tube, and it provides much stability because of its construction. But in case of Cassegrain, the tube is not very large due to multiple reflections happening inside the happening after the light striking the primary mirror. The effective focal length is increased. Though, so if we have a telescope with 1200 millimeter focal length, suppose a Dobsonian would be about 1.5 meters long. And if we have the same focal length Cassegrain telescope, it would be about 1 or 2 foot long. That's it. So Cassegrain are much more compact in the size in compared to Dobsonian.
Okay, thank you, Rishabh. I hope that clears the query. And one last question is that suppose someone has to buy his or her first telescope. So will a reflector be a good option or the refractor telescope?
Yeah, so if someone wants to buy a telescope, and supposing that he or she does not know much about using telescope, so I would recommend to start from the refractor ones because they are much easy to use, as Rashmi told in her slide, that you can move them in any direction without any specific alignment. But in case of reflectors, Newtonian telescope, we need to make polar alignment. So I think, I personally think that it can be tough for a beginner to make polar alignments easily without any guidance or so. So I suggest that one should start with the refractors of an average size, like 70 to 80 refractors will be good.
Thank you, Rishabh. Thank you so much. Over to you, Shankar.
Thanks, Rishabh, for the wonderful talk. So, in our this session, the next speaker is Srijit. Srijit is from Aditya Engineering College. He is doing his BTech, and he will be presenting on Panspermia and alien speculation. So, Srijit, you can start sharing your screen.
Hello.
Yeah, we can hear you, Srijit.
This is Sujit. My topic is pan.
Sorry to interrupt, but you need to speak a little bit aloud because your voice is a little low.
Panspermia is a theory in order to answer the questions of us like what is the basic structure of planet and many other questions like that. Don't have perfect answer for our question how did life form on earth. So hypotheses and theories and in one is panspermia. Panspermia is but only only transportation of life elsewhere part in the universe to earth. Scientists physicists like Carl Sagan involved in these ideas. Primary idea is that existing elsewhere in the universe is came here to with asteroids and comets or microbial. So having a chance to travel through interstellar spaces by getting inside asteroids. So there are many types of panspermia. One where we're discussing about radio direct and pseudo. Radio panspermia is an easy concept, and understand this. Let's imagine a planet with atmosphere where we have microbes at high levels of there due to the radiation of star radiation pressure or even winds, solar winds. Microbes flown away of the and if another planet or beyond the planet can survive life, the life would start growing again on our moon. So this we know microbes survive extremities of temperatures in space like plus or minus 400 to severe. You know this figure shows which is to very nations known to us. It can survive many months, and this support this concept. And panspermia, lithopanspermia is mostly accepted and very logical to believe in this. As you can is consider this planet contains some life and asteroid hitting it, so the life inside this planet along asteroid and it for of years to maybe and hits a host planet and then it resumes its living. So many oppositions came from this concept that how did the life survive without light or heat, we get things frozen, right? So it's the same way life gets inside these asteroids, and after reaching there and one more thing is accidental, or it's called, or it's also called directed us and our seeds in this planet. This is very interesting, and Francis Crick, the scientist who got the Nobel Prize for inventing DNA structure, that this might be a cause for our planet's living, and Earth could be dumping yard for life. Know yet how functions or aliens there or not. So how do we believe in this panspermia? Don't have any accurate answers for formation of life or planet. This might be an option, and USA recently confirmed that UF real, and we have more than 3 to 4 thousands of exoplanets. Many unexplainable radio signals from outer space, like the wow signal in 1970s, caught our attention on that we are not be alone in this universe. Many other being might exist elsewhere in the universe. So this quote from Carl Sagan, absence of evidence is not evidence for absence, concludes this. Thank you. Questions are open.
Thank you, Srijit, for this talk. So we have a question for you in the chat window. It is, does the existence of tardigrades prove the factor of existence of alien life in space?
Yeah, but we have discovered any alien life, but tardigrades can meters of temperature. So we think aliens life. We still don't know how life functions. what exactly for us, our life should have water, atmosphere, and suitable temperatures. For other alien beings, it is not the case.
Okay, thank you so much. Over to you, Shankar.
Thanks a lot, Rishabh, and thanks a lot, Surajit, for having this wonderful talk. So you can stop sharing your screen. And for the next talk, I would like to invite Shifana. So she's doing her MSc Physics second year, and she is from Cochin University of Science and Technology. She's going to present her talk on correlations between CME parameters and sunspot activity in cycle 23 and 24. So I would like to invite Shifana to share her screen and give us the wonderful talk.
Hello, am I audible now?
Yes, you are audible, Shifana.
Okay, thank you. Today I will be giving an introductory talk on the topic correlation of CME parameters with solar activity. And this will be okay. First of all, I would like to give an overview of my presentation. First of all, I will like to give an introductory lecture on the topic what does CME and why do we have to study them. And next, I would like to give an idea about sun and solar activity. And later, I will be discussing on analysis and results of my study. And then after that, I will be discussing about the conclusion and future scope of the study. So, what is coronal mass ejection? Coronal mass ejection is nothing but a large, huge burst of plasma and magnetic field from the solar corona. It is because of the instability of the magnetic field of the solar corona, and due to sun's differential rotation of the solar corona, differential rotation, the magnetic field reconnects and it bursts out of the solar corona with a high velocity. It will be accompanied by solar wind, solar flares, prominences, etc. In the study, I am used Soho-Lasco data, and in the right hand side you can see a picture of CME recorded by Soho in March 13, 2013. And in this picture, you can see it is a loop-like structure coming out of the solar corona. And now, why we have to study CME? CMEs are of both scientifically and technically of importance because, as we all know, Sun is the greatest experimental lab to study plasma physics, and when the huge amount of plasma and magnetic field are ejected out of the solar corona, it interacts with the Earth magnetic field, and it creates a beautiful spectacular atmospheric displays known as aurorae in north and south poles of Earth. And of course, as this large amount of magnetic field and energetic particle are ejected into the interplanetary medium, it will affect our Earth power grid lines, and it strongly affects our communication system, satellite system, etc. So it is very important to constantly monitor the dynamics of sun in order to predict the space weather. So that's why we are constantly interested in CMEs. And next, I would to introduce about sun and its solar activity. As I mentioned earlier, CMEs are greatly associated with the magnetic field of sun. So in my study, I considered sunspot number as a manifestation of magnetic field of sun. So sunspots are nothing but a cooler a region of sun's photosphere, and it appears to be dark. It is of high magnetic intensity field. Due to differential rotation, the sunspot number keeps changing in a day, and it follows a 11-year cycle known as solar cycle. So in my study, I considered the sunspot number cycle and CME parameters and trying to explain these relations between these two so that we can predict the behavior and characteristic of CMEs. And in my study, I have used CME parameters such as linear speed, quadratic speed, angular width, acceleration, central position angle, and detection rate of CME parameters. Linear speed, I meant that linear speed means it is obtained from the linear fit of high time measurement of CME. Quadratic speed is obtained from the high time measurement quadratic fit. And angular width of CME is obtained in degrees from the two edges of the CME. And the detection rate is measured timely, and the data available from the Soho LASCO website. And first of all, I am trying to correlate between the detection rate and solar cycle. In the right hand side, you can see a graphical representation of the CME detection rate with the monthly, with the fraction of the decimal year in the x-axis, and y-axis I have plotted both CME detection rate and sunspot number. And from the figure, it is also very clear that it is highly correlated. And I have used a Pearson correlation coefficient to calculate how these two parameters are related. And in my study, I have concluded that the detection rate and solar cycle is highly correlated, with the correlation coefficient of 0.614 in solar cycle 23 and correlation coefficient of 0.899 in solar cycle 24. So excitingly, these two parameters are highly correlated. And next parameter I chose is the linear speed, which is obtained from the linear fit of high time measurements. And this is also highly correlated with the solar activity, with a correlation coefficient of 0.68 in solar cycle 23 and 0.71 in solar cycle 24. And the second order speed and solar cycle is also correlated. From the graph, it is clear that the cycle 24 has the greatest correlation, with the correlation coefficient of 0.65 and 0.58. And I forgot to mention that the solar cycle is 11-year cycle, and the 23 cycle lasts from 1996 to 2008, and 24th cycle is extending from 2008 to 2020. And of course, we are in the end of the solar cycle 24, and the cycle is a pretty much long cycle than 11-year cycle. So next parameter I'll choose is angular width of the solar cycle of the CME and solar cycle. Angular width is also highly correlated with the sunspot number. From this, we can conclude that if a sun is of high magnetic activity, then it will burst out a very wider CMEs. Next parameter is acceleration. Acceleration is surprisingly anti-correlated with the solar activity. That is, when a sun is of high magnetic activity, it emits a kind of decelerating, accelerated particles or CMEs into the interplanetary medium. So now I would like to conclude with a few topics of my presentation, which I have obtained from this graphical representation. First of all, it is a linear speed which is highly correlated with the sunspot activity. Detection rate is highly correlated. Second order speed, which is obtained from the quadratic fit, is also highly correlated with the solar activity. Acceleration is somewhat anti-correlated with solar activity, and with this a very small correlation coefficient. And next, I'm sure that my presentation will be incomplete without mentioning about India's first solar mission, Aditya L1. And you can see a picture of Aditya L1 and of the instruments associated with the Aditya L1, and hope it's launched in 2020. And this will provide more information about the solar corona and a better understanding of solar corona and CME, and hence space weather predictions. And of course, the funding agency is ISRO. And hope this talk's helpful. Over to Q&A session. Thank you.
Thank you so much, Shifana. That was really a wonderful talk. So one of the questions is, the other day I was reading an article on some of the unsolved mysteries in the universe, and one of them was the solar cycle. So the question is, what exactly this solar cycle is, and how far are we in solving this mystery behind the solar cycle? What causes it?
The basic explanation of solar cycle is due to sun's differential rotation. That is because the different layers of sun is rotating with a different speed. So it creates, due to differential rotation, it creates some cooler parts in the sun's photosphere, which is known as the sunspots, and which is of high magnetic activity, and hence the plasma cannot enter into these pores, and hence this is of cooler part. And the sunspot number will be giving idea about how magnetically active the sun is now. And this sunspot number is tracing a cycle of 11 years, which is from the solar minimum, and it attains a maxima, then it is coming to a fall in its magnetic activity. That is what it is going in a solar cycle.
Thank you so much. Thank you so much. Over to you, Shankar.
Thanks, Rishabh, and thanks, Shifana, for such a wonderful talk. So, in this session, we have our last speaker. So, we have Sejal with us. He's from Sri Venkateshwar College, University of Delhi, and he will be giving the talk on ion Coulomb explosion of spherical clusters with varying charge density. So, Sejal, you can start sharing the screen, please.
Hello, am I audible?
Yes, you're audible, and
And
we
is
can
my
see the
screen?
screen as well.
Okay, so the topic of today's presentation is ion Coulomb explosion of spherical clusters with varying charge density. I hope you do not mind me not sharing my video. Is that okay?
Yes, that's completely fine.
Yeah, okay. So today's topic is ion Coulomb explosion of spherical clusters with varying charge density. Although this topic is related to some plasma phenomena when an electromagnetic wave interacts with the plasma, but there are some specific uh, characteristics, or we say we have taken some specific type of electromagnetic waves and some specific plasmas in which we have studied this particular phenomena. So beginning with this, I would first like to introduce about the plasma as a fourth state of matter. As we keep on increasing the energy of a particular substance, its state changes. For example, if we heat ice, we actually provided energy, it transforms into liquid water, and then providing more energy, it transforms into gaseous state. So similarly, when to a particular state of matter, we provide energy through different means, there comes a point when the two charges, which is positive and negative charges, they separate out but still exist in the same spatial region. That particular state of matter is known as the plasma state, which is very peculiar and is being studied these days because of its some of its very unique properties that are not shown by the rest three states of the matter. Certain properties shown by this state are basically because of coexistence of both the opposite charges in the same spatial region. Also, there is one more very important point about this state, that if we place this particular matter in some space, in some volume, then overall charge on this volume may be zero, but in spatial differential regions, the charge may or may not be zero, which gives rise to several internal electric and magnetic fields, which actually show different, because of which it shows different properties in interaction with external fields. So the the process that we have actually studied is the Coulomb explosion. So to understand this, we actually try it as visualizing two spheres, which are again made up of smaller spheres. Now, one of this bigger sphere is made up of smaller sphere of ions, and the other is made up of electrons. These two spheres are such that when placed over one another, they actually fit so well that we cannot even distinguish between them. That is this that this overall sphere is neutral. Now somehow we provide energy such that the electron sphere moves out of the ion sphere, leaving behind that positively charged sphere, which undergoes interionic repulsions, and the ions of this sphere start moving apart from each other. Now this process in which uh, after the ejection of electron sphere from this ion sphere, the unutilized ion sphere undergoes repulsions, and the ions start moving apart from each other, gain energy, and also in this process, when these ions gain energy, they interact with each other and the ions around, also with the neutral atoms which do not undergo these this ionization or electron removal. So they interact with each other, they undergo several reactions, and in the process, neutrons as well as X-rays and other high energetic rays are ejected out, which actually made this a very important process to be studied to know for various phenomena occurring all around our universe. So, interaction of laser pulses with plasma, uh, they interacted very, they interact actually in a lot of ways. So, as I actually mentioned that after interaction, several neutrons can be produced. The electrons that actually get removed from the ion sphere also accelerate. Also, several X-ray radiations are generated. Also, this is one such phenomena in which we actually provide a very small amount of energy and it gets transferred to the ions, and then it is kind of transferring one photon of energy into a number of into very large amount of energy distributed over several ions. So this process is actually transferring of ions from transferring of energy from electromagnetic waves to the material ions. So basically, from where this began was this is a very famous experiment by Dittmeyer. He observed that when there were clusters in a gaseous volume and they got ionized by and the laser was sent into that volume, 95% of the laser energy got absorbed, while when the clusters were not present in that specific volume, only 5% of the incident laser energy got absorbed. So this was very astonishing to notice that just by the presence of clusters, the absorption amount increased by such a large the absorption increased by such a large amount. So this actually drove attention of scientists from all over the world, and they tried to actually uh, build up a background theory for how it is actually happening. So this theory also began with Dittmeyer and his companions. So what he did basically was to study this particular process and give his own theory. So these are some prior studies that are mentioned here. So they actually modeled to explain the experimental findings of this process. There was Michelberg who developed one-dimensional code. There was Zubek who developed theoretical model of collisionless ion Coulomb explosion. Also, Professor C.S. Liu and Dr. V.K. Tripathi, they also modeled some different conditions of these particular phenomena. So basically, now this tunnel ionization of electrons by a laser is the main beginning of this process, which is the removal of electrons from that ion sphere particularly. So as we see in this figure, there is this black potential well, which is the actual potential well in which the electrons are present. Now this red line is the laser electric field, which drastically modifies this black potential well and gives it the green potential well shape. It becomes easier for the electrons to escape out of this green potential as compared to the black potential, because the probability of the electrons escaping out of this green region is much higher as compared to the black region. So as a very small uh, duration Gaussian laser pulses incident on these clusters, they tunnel ionize the electrons and leave behind the positively charged ion sphere. So this current, basically what I did on this is modeling of the clusters completely depleted of electrons. That is, the electron sphere has completely left the ion sphere. The other condition could be that it partially release some of the region of ion sphere can be neutralized by the electrons, and therefore only the left region would experience interionic repulsions. But what we have done is we have considered complete evacuation of electrons, but we have considered varying charge density. Dr. C.S. Liu and Dr. V.K. Tripathi Dr. V.K. Tripathi is a retired professor from IIT Delhi. So following his paper, he actually considered partial evacuation of a cluster with constant density. But following him, what we have done is complete evacuation with varying density. So this is the glimpse of the study that we have followed basically from Dr. V.K. Tripathi and Professor C.S. Liu. So calculating the field, electric field experienced by the ions at different positions when they start moving from each other, and how the energy gained by the ions varies, and the ion energy distribution function, which is what number of ions gain energy at what rate, and the number of neutrons that can be produced out of the interactions taking place between them finally, is what was the motive of the study. So this is the beginning, from where we have actually incident a femtosecond duration Gaussian laser pulse on a volume consisting of deuterium gas clusters, which this laser tunnel ionizes these clusters, and they in turn undergo ion Coulomb explosion. So I guess these are the actually equations that we have derived for the fields, as well as fields experienced by the ions, as well as the energy gain. And this final Fe is the ion energy distribution function, which is actually calculated on the basis of the studies that we have we could actually find, and the basic theory that we followed. So this is a graph that we obtained plotting initial radius versus the initial energy gain. So as the ion sphere get completely evacuated of the electrons, and they experience interionic repulsions, they start moving away from each other. As they start moving, they gain energy. So if we consider ions initially at radius Ri, for from 0 to R naught, which is the radius of the cluster, the ions at different positions will have different energy gains. So this is the kind of plot that we got. So and this is the number of ions with the initial energy gain. We have actually considered several parameters from n naught, which is the number of ions in a cluster of the orders of 10 to the power 22. So the neutrons, after interaction, the neutrons that could be generated out of it was of the order of 10 to the power 5. This number actually states how important this particular process could be if it is employed to produce neutrons, and these neutrons could be actually used for various laboratory experiments, which is also being done these days. Also, there is this another density variation which we studied. This is also similar grounds like the previous one. One very important thing that we noticed was that the energy that this variation of densities got this we actually studied that the in both the cases, and but in this case the neutron estimation was very was higher actually compared to the previous one as well. So it was actually higher than the previous one, where in the first case it was 10 to the power 5 only. Here we get 1.5 into 10 to the power 5 neutrons. So this is the comparative analysis, which actually shows that the type of plots are very much similar for both the cases. The results in conclusion actually are about the equations that were derived to generate these plots. So I would like to end it here.
Thank you, Sejal. Thank you for this talk. So I have two questions for you. One is directly related to this talk. That is there any astrophysical implication of this Coulomb explosion?
Rachel, can you hear us?
Yeah, I can hear you.
Yes,
No,
we
I was
calculate
talking.
the neutron number. They are for the deuterium gas, and the final yeah.
Yes, there was some problem with your internet, Rachel. So yeah, please continue. I think there is some internet connection issues over Sejal's end. So I would like to end this session now, and I invite Dr. Bindya Arora to give some remarks before the start of the next session and the poster session.
Thanks a lot, Shankar and Rishabh. It was indeed a very wonderful and smooth session, I would say. There were some technical glitches because of the internet issues at the speaker's end, but I guess it's technology and it's not always reliable. So this is the end of the first session, and we'll take a 1 hour break for lunch, and we are going to keep the Zoom on. The meeting is still running. We'll all see you at 2:30 now with the last session of the conference. I'm sorry, I forgot to mention the poster session is... I'm sorry, Shankar, I just forgot to make a small important announcement that the poster session is now live, and the YouTube link which we have shared with the participants, in the comment box you can click on the website for the posters, and you can scroll down and see all the posters we have for the conference. If you want to interact with the presenters of the posters, then you can always use Slack account to talk to them and ask your questions. In any case, if you have any questions regarding to poster, you may also comment them in the chat window of YouTube. We'll try to keep account of as many questions as possible, since there are a lot of spamming in the YouTube chat window. So we might miss a few questions, but if you have, in case have some question, you can always connect us through our WhatsApp group or on the YouTube chat window. Okay, so I request you to please kindly have your lunch and maybe go through the posters once. Thanks a lot. See you at 2:30 now.
I'm not able to hear you, Abhijit.
Abhijit, you are not audible.
Am I audible now?
Yes, you are audible
Yes,
now.
now you.
Sorry, it was a glitch from my side. So very good afternoon to all of you. I welcome you all to the second session of this e-conference, AstroRetreat20. So in this session, we will have 6 to 7 oral presentations coming up now. The guidelines for the session will remain the same as the previous one. That is, each speaker will be getting 6 to 8 minutes to present his or her views, and then there will be a short Q&A session. The questions will be typed in the YouTube chat window, will be raised by our co-host, Ms. Priyambada. So wasting no time further, I would like to invite Lakshita Bageja from Sri Venkateswara College, and she will be discussing about nuclear interactions. Over to you, Lakshita.
You need to unmute, Lakshita.
Yes, ma'am.
Hello, am I audible now?
Yes, you're audible.
So I'm just
Please start your screen sharing.
So if you have my PPT, can you please share it for me? Because
wait a minute, I will have to download it first.
I'll try to do that from my end, Abhijit. Excuse me.
Yes, ma'am. Yes, ma'am. Please do that for me.
Lakshita, your number was OP7?
Yes, ma'am.
Yes, ma'am.
Unfortunately, I don't have your on my system. I'll get it from the account itself. Just a moment. Okay. So I'll be sharing the screen now, Lakshita, and just let me know when to
change the page. Yeah, of course.
Okay. I'm sharing my screen now. Yeah, is the screen visible to everyone?
Yes, ma'am, it's visible to me at least.
Yes, ma'am, it's visible.
Please go ahead, Lakshita.
So now we'll basically understand what is nuclear interaction. Nuclear interaction is very important to analyze and interpret the behavior of the early universe, and as well go to the synthesis of higher elements. So nuclear interaction is comes up with, ma'am, please change the slide. You change the PPT basically.
Yes, I changed the slide. Okay, I'll move forward. I'm so sorry. There's something wrong with the... please give me a moment so that I can download your slide. Okay, so I have it now here. I'm sharing the screen again. Okay, please, Lakshita, go ahead.
So to basically understand the nucleus and its importance, it's important to analyze its properties, like what is binding it together and how that bound system, which a single nucleon cannot exist by its own. As we know, a nucleon, which is basically a proton or a neutron decomposes into its constituent particles. But in a nucleus, they are bounded together, and there are many models which predict these binding energies. So there are also nuclear interactions in which there can, when a nucleus is interacted or scattered by another nucleon, there can be two kind of basically reactions, direct and compound, and there are various reaction mechanisms that follows, like the elastic and inelastic collisions, which then gives us the understanding and applications of the strong interaction that exists between those nucleons and within the nucleons. So there are two basic interactions called the residual strong force and the main strong force. Then we come to the analysis of super heavy elements, in which there is an island of stability, which is very pioneering research topic, and which has the problem of fermium hole, according to which beyond a level no super heavy elements can be formed, and forming those elements helps us analyze the early universe. Now we get to, if we understand the nuclear properties are primarily attractive, they are non-electric, and they are non-gravitational. Non-gravitational means, if we compare the electrostatic ratios to the gravitational ratios, we find out that there is a large number, which implies that gravity is negligible in compared to electrostatic force. But when we consider electrostatic and strong interaction, we therefore realize that strong is much more stronger than the electrostatic repulsion. If a basic proton-proton interaction is considered within the nucleus in a range of around 1.5 femtometer, we realize that a force of 230 newtons is required. Such an extreme force is small as compared to the strong force. So strong force turns out to be very large as compared to gravitational. Now, the nuclear forces are also repulsive deep inside, and this is predicted by their non-centrality. So if I consider this graph, what I realize, but after a certain limit, that is usually 1.2 to 1.8, there is a repulsive core. That means all the nucleons, though having a strong force, do not fall or become a single entity because of this repulsive core. And the strong force, it decreases down going to the higher distances. So it has a property of saturation. It is charge independent, and it's but turns out to be spin dependent. This spin dependent properties are basically predicted by considering the neutron scattering, in which we get different scatterings for different spin values. Now, if I get deep into the nucleus, what is binding it together? There are various terms which bind it together. First of all, the volume term, that is the basic volume. So if there is number increase in the number of nucleons, its volume term remains constant. The binding in that specific volume is constant. But its surface term, with an increase in nucleons, the number of surface terms increases, and hence I need to subtract a surface term from the binding energy, followed by the Coulombic repulsion between protons, and then followed by the symmetry. Symmetry arises basically due to the Pauli exclusion principle, and there are various models which predict these. First of all is the Weizsäcker model, which uses a basically liquid drop. Then comes the shell model, collective models, and so on. There is independent particle model, compound nucleus model. Next slide, please. Now, while considering reaction and interaction of nuclear particles, important thing that comes is the backscattering. What actually is backscattering? In backscattering, when I have a proton target and I bombard neutrons towards it, what I observe is, at central region, that is around 0 degrees, I get a high maximum, which decreases when I increase the angle up to 90 degrees. But beyond that, after certain angle, what is observed, there again a increase in the peak of the nuclear cross section. And how that is accounted for is basically due to the backscattering phenomena that takes place. Backscattering is the exchange of pions, which transforms the proton into neutron and neutron into proton, and this is the basis of the strong nuclear force that we shall now study. Reaction mechanisms. There are various possible reaction mechanisms. When a nucleon is interacted or a neutron neutron is thrown at a nucleon, there are three possible reactions that takes place. Either the neutron can be elastically scattered, or it can have a quasi-elastic scattering in which some energy is used to scatter, deviated from its path, and some is used by dissipated. Whereas there can be a process of deep inelastic fusion in which this DIP signifies that deep inelastic fusion, in which there is inelastic scattering seen, in which energy is not conserved, and that energy is used to raise the original nucleus to a higher nucleus level. Or there can be fusion. We know fusion is basically interacting of two nucleons. When we throw or bombard neutrons in it, it can either fuse also towards the nucleon, forming a higher compound nucleus. So in this reaction mechanism, there are two types, that is direct and compound. What is direct and what is compound? Direct usually takes place at higher energy when a nucleus is probed by means of bombarding the nucleons with high energy. What we get is on the surface, the projectile nucleon on the surface interacts and hence turns towards a forward peak, reacting with only surface molecules. Whereas there can be a compound nucleus formation, which is basically fusion and takes place at low energy, and which considers the mean field of the nucleons, which is more isotropic, that is, it extends towards all directions. Next slide, please. To our base, to more get deep into the understanding of nuclear interactions, we know quarks are very important. Quarks are the constituents of the nucleons, and as we shall see, the interaction within the nucleons and between nucleons is due to this quark interaction. These are the stable particles. There are more particles that exist within protons and neutrons which have a relatively shorter lifetime, but these are stable, so these are renowned ones. If I consider the strong force, in strong force, there is basically quantum chromodynamics that studies it. Quantum chromodynamics is this interaction based on their color charges. Similar to the normal electric charges, we have color charges considering the strong force, and this just have a basis of neutralizing, hence forming a white color. If I consider mesons, they are quarks and antiquarks. If they are baryons, baryons are from composites of 3. And hadron masses do not depend on the dynamics, but just on the quarks inside it. Next, please. So strong interaction is of two types, fundamental and residual, in which we have experiencing particle quark gluons or hadrons, and these takes place within the nucleus and between the nucleons. And this nuclear interaction finds a very important role in early universe, because if we want to know the history of the early universe, we can produce it on a microscopic scale through these heavy ion reactions and create high baryon states. There is also an island of stability which can be achieved through these high interacting proton or nucleon scatterings. Fermium hole, as I've already explained, is the point beyond which the synthesis of super heavy elements through beta minors and fusion processes are not possible. And at last, I'd like to put a view on the exotic states in which we get a quark bound states. Like a baryon has 3 quarks or a meson has 2 quarks, there can be tetra quark or dibaryons with a 4 quark system or a 6 quark system, hence leading to exotic states with high baryon, with high quantum states, quark matter. Thank you.
Thank you, Lakshita. If any of the participants want to ask any question to the speaker, they may go ahead. If nobody is having a question, can I ask you a question, Lakshita?
Yeah, of course.
Yes, I wanted to know what are your views on the grand unification theory, which talks about unifying all these forces?
I I think yes, grand unification is there, because if I relate everything with fields and everything with electronics, with some space field associated with it, even matter particles, when escaping through the space fields, create a vacancy, which is nothing but the antiparticle, as we have already known through quantum electrodynamics. And this antiparticle and the anomaly of lesser number of antiparticles maybe is due to the fusion dissipation of that antiparticle energy into the whole system, like we study in the hole and electron configuration in our semiconductor studies. And there is an uncertainty which in that uncertainty in its mass expands throughout entire space and gets towards the boundary of the exterior point. What I want to tell is, there is a field concept. If I can relate it to everything, so that field concept will give me the unification of every forces.
Thank you, Lakshita. I had seen that OP9 had their hand up. You may proceed to ask the question.
Hello,
Yeah,
am I audible?
yeah, you're audible.
Okay, so I want to ask that is particle exchange necessary for having an interaction? Like you mentioned, in the nucleons, there is strong force which are based on the exchange of pions. Actually.
Yeah.
So is it necessary to have exchange of particle for any interaction to happen, or interaction can happen without exchange of particle also?
What we actually realize that any force that exists in our surroundings is maybe contact or non-contact. And if I get deep into every kind of force, there are gravitons and photons predicted, which are the force carrying particles, which it relies on the theories on the basis that interaction takes place through these oscillating particles that transfer or changes from one constituent to other constituent, hence releasing the force as it is predicted by a throwing of ball. Like for throwing ball, you need to be in a certain range for that throwing process to continue. So in the same analogy, it is being put forth that exchange of particles is necessary for the matter or any constituent on which force is acting to remain in that specific range.
Thank you, Lakshita. Since there are no questions anymore, I request my co-host to introduce the next participant, and I would like to thank Lakshita for her wonderful talk.
Thank you.
Proceeding further, I would like to bring to notice the fact that we are already running ahead of the time, short of time, and I would request all the participants to keep their talks a bit shorter so that we can have the questions properly at the end. So moving on further, I would request Shantanu Das to come up. He's from Dayal Singh College of University of Delhi, and he will be talking they want to see. Shantanu Das, I'm unmuting you. Over to you now. You can share your screen now, please.
Everyone, am I audible?
Yes, you are audible.
Okay, so speak about how particle accelerators see the particles they want. So, as the name suggests, a particle accelerator is basically a device which accelerates particles to very high velocities and energies. Now, the very first particle accelerator that can be named so is J.J. Thomson's cathode ray that accelerated electrons that were called beta rays to a high velocity magnetic electric fields. Now, in the evolution of particle accelerators, the next significant particle
I'm sorry to interrupt, Mr. Shantanu. Your voice is not clear. Can we just? Your voice is cracking a bit.
Now is it fine?
It's better, I guess. Please continue.
Okay, so the next one is Van de Graaff generator. It is not exactly particle accelerator, but it still accelerates electrons using only electrostatic force. The next significant particle accelerator, that is the three-module structure to the particle accelerator to predict the cyclotron that was invented by Ernest Lawrence. And the cyclotron basically accelerates particles in a certain using perpendicular electric and magnetic. So now we have come to an age of particle physics where the largest scientific device is actually particle accelerator, Large Hadron Collider, which is like the most famous particle accelerator, the Higgs boson. So now I'll further tell about how exactly these particle accelerators tell about the property of particles we are investigating. So the topics are basically scattering that my previous the previous talk talked about scattering of particles, and then I talk about process. Now imagine there's a hard there's a target spherical and a projectile is bombarded. So naturally find that it will collide and bounce off at an angle theta. So and that angle theta depends basically upon how the potentials or how the projectile and target interact with each other. So hence the potential is actually zero when the projectile is a distance r away, more than a distance r, and the potential is infinity when the projectile comes inside the distance r. So basically, a projectile bounces off the target at exactly the distance r. Now, beta and the calorimeter beta, it is the distance of the projectile from the target, or now a more better idea in fundamental physics is we are not exactly colliding one-on-one particle. So what we are doing is we are colliding multiple. We have multiple targets. We have multiple projectiles to provide them. So let us consider an area, a thin foil maybe, which has a total area of A, and every small target has a basically the geometrical cross section of sigma. So and the density of particles in that foil is so if P is the probability that projectile hits the target and that can be said as the total amount of area of the target by the total amount of area of the whole foil. So that comes out as beta sigma. Now B can also be said to be the ratio of the number of total projectiles to the total number of projectiles fired. That gives the scattered projectiles, total projectiles, the density of the foil, and the cross section. The scattered number, total number of scattered projectiles can easily be found experimentally, and the total number of projectiles. This is not so. The scattered cross section can easily be found, and that gives us an idea about the dimension of the target particles we are bombarding. But practically, we are doing things in 3 dimensions. So we define a unit or term called differential cross section. Actually, the unit amount of cross section per unit amount of solid angle. That's called differential cross section, and it gives an idea of how much amount of solid angles the scattered particles make is to how much the cross section of the target particle is. The idea of this scattering process was used by Rutherford in the famous Rutherford scattering experiment, that is performed by Geiger and Losbeth. Rutherford interpreted that the alpha particles that bounced off the gold plate and he found out a relationship between the scattering angle and cross section of the nucleus. With this, he was easily able to find out that the dimension of the nucleus was about 1 Fermi in diameter. Next, we see that according to the wavelength of particle is inversely proportional to its energy. So we can easily see that higher the energy of a particle, the more the shorter its wavelength will be, and the better we'll be able to probe the target particle. This was done by Nobel laureates Hofstadter and Rosenblatt. You can see the papers here. Now, at last, I come to the fact of simulation, Monte Carlo simulation. So, whenever we think about the LHC, whenever we see some videos about it, we find we talk about simulations, how the particles will collide, how they scatter. So, what exactly are Monte Carlo simulations? So, the Monte Carlo simulations refer to any method, any simulation that makes use of random numbers and uses probability statistics to solve some problems. So these are basically used in forecasting weather, experimental apparatus, in simulating experiments, and in numerical analysis of things.
Excuse me, Mr. Shantanu.
Yeah.
We are not able to hear you now.
You're not able to hear me?
Now we are able to, but now it is audible.
Previously, you were not able.
For a brief time only, like 2-3 seconds only. Start, please. Start, please. Continue.
Okay. Okay. So, so basically, in the scattering experiments, it is not exactly one particle that is in one target. So the observable phenomena, the observable variables, not exactly tell us about the properties of matter. So what we need to do is we make scientific models or we assign random numbers to calorimetric properties of particles. These properties then, using Monte Carlo simulation, give us certain observable variables, and comparing those observable variables with the real scattering experiments, we are able to find about the particle characteristics like charge, density, mass, etc. So, on an average, particle physics is basically generating new models and simulating these using Monte Carlo experiments, and then comparing these with the real experiments, trying to find out the properties of matter. Thank you.
Thank you, Shantanu. If any of the participants have any questions, you may ask them now. I think we can proceed to the next talk.
Yes, sure. So, first of all, I would like to apologize to all the participants. There were some glitches from, I think, Mr. Shantanu's end, that we couldn't hear the voice property. His voice was cracking a bit. So I apologize again from the whole conference committee itself. So in the next oral presentation, we have with us Mr. Harsh Pratap Singh from Kirodi Mal College. Due to some tech issues, he had sent us a pre-recorded video, which will share the screen and play alongside. In addition to that, we have him here at present. So the audience may ask the questions and type the same questions in the YouTube chat window. So the title of his talk will be Equivalence Principle and its Consequences. I will be sharing my screen now.
good afternoon to everyone. Myself Harsh Pratap Singh from Kirorimal College, University of Delhi. So I am here to present on the topic equivalence principle and its consequences. So equivalence principle is the very important principle given by Mr. Albert Einstein in 1907. So he had given this principle to formulate the general theory of relativity. So basically Einstein has already formulated a special theory of relativity, but the defect was that it was only applicable for constant speed and it was not applicable for acceleration. So he had to introduce a general theory of relativity which is generalized for the accelerated frame of references as well as non-accelerated frame of references. So basically let us have a little idea about equivalence principle. So it basically describes that suppose we are having two observer, one observer in an accelerator which is there in outer space without any gravitational effects on it, and another observer is in an elevator which is freely falling on the in the surrounding of the earth under the gravitational effect. So both these observer cannot tell the difference between the two situations without seeing outside this elevator because both of the effects are same. So we can say that a falling man cannot experience gravitational effect on it. So now why there is a need for introducing a new theory of gravity. So Newton formulation of gravity doesn't mention about time. So you know that Newton has given the formula F is equal to G m1 m2 upon r square, where this is the force between two masses m1 and m2 separated by distance r. So that formula doesn't talks about time. That means how this effect is traveling from one mass to other mass. So at that time it was assumed that this effect is traveling with infinite speed, but after special theory of relativity it came into existence that it will be violated if this effect or if this physical effect is traveling faster than speed of light. So according to Newton equation, the effect of gravitational force is instantaneous. So it leads to the contradiction of special theory of relativity. And so there is a need to reformulate gravity, and that's why equivalence principle came into existence. So now came the happiest thought of Einstein life. So what Einstein was imagined that a man falling from a roof of the house, at least in his immediate surrounding, cannot experience a gravitational pull. So basically the statement of equivalence principle says that the inertial mass and the gravitational masses are equal. So first of all, let us talk about what is difference between inertial mass and gravitational mass. So inertial mass is the mass which have to tell the object that how to behave in an accelerated frame of reference, and a gravitational mass is the mass of an object when it is put under the gravitational effect. So these two masses are completely given by different theories, one given by inertial and other given by gravitational theory. So these two masses are equivalent, that was given by the equivalence principle. So the principle describes the equivalence of acceleration and gravity. So the general theory of relativity came into existence, and it is the consequence of equivalence principle. So now special theory of relativity versus general theory of relativity, that means we are just comparing the STR with GTR. So the special theory of relativity talks about inertial frame, and it says that all inertial frame are equivalent, or we can also say it is one of the postulate of special theory of relativity that the physical laws are same in all inertial frame of references. And in general theory of relativity it says that inertial and gravitational masses are equivalent. So both talks about the equivalent of something, but they are completely different. One talk about the equivalence of constant frames moving with constant velocity, but another describes about the equivalence of gravitational and inertial mass. So the gravitational field has only a relative existence because for an observer, at least in his immediate surrounding, does not feel any gravitational existence or any existence of gravitational field. So basically what this particular statement means is that observer falling from the roof of the house, at least in his local surrounding, that means equivalence principle is only applicable for local surroundings. So now there is a statement which equivalence principle has given. It gives the equivalence of acceleration and gravity. So is gravity a illusion only, that it's the effect of acceleration only? So of course it's not, because gravity is somewhat different from, little different from acceleration, but we can differentiate between these two things when we are considering large frame of references. For local frame of references, these two effects looks to be same. So now the question arises then, how to differentiate between acceleration and gravity. So differentiating between acceleration and gravity, so here we are taking two objects, like we have taken two apples here. They are separated by some particular distance, and when they are falling under the influence of lunar gravity, so these are moving in a path conical, in this path of conical. So the separation between these two objects is decreasing with time. But if we imagine a big accelerator and these two objects are put at their ends, and that is accelerated with some acceleration which is equivalent to the lunar gravity, then they will fall in this pattern, like cylindrical surface pattern. So that will that means that their separation is not a function of time. So we can differentiate in this way in acceleration and gravity. So now effect of gravity on light, excellent consequence of equivalence principle. So how acceleration leads to bending of light. So we can understand this beautiful fact using equivalence principle. So to an observer in inertial frame of reference, light is having a rectilinear propagation. But for an observer in the accelerating frame of reference, the light is bending. So how can we take this effect into account? So we can consider this effect by considering an elevator, and a person shines a laser into that elevator or some light beam, and a person standing outside will going to see that the light beam is going straight, like this. You can see here the light beam is going to be straight, but it is the bottom of the elevator which is moving upward. So a person inside the elevator will going to see the bending of light, but it is not actually happening there, because of course someone think that the observer outside is right because inside is just having an illusion only, but it's not correct according to general theory of relativity. It says that both are right in their frame of references. So the story changes with the frame of references. So this is the effect of acceleration on the bending of light. So we can easily transform that effect to gravity by using equivalence principle, as we say that acceleration and gravity are the same thing for the local frame of references. So we can say that light bends in a gravitational field. So that is the transformation effect of the gravity, and this phenomena is called as gravitational lensing.
So the video has ended. We have
Yes.
Yes, please.
If there are any questions, then the participants can ask. Maybe we should proceed to the next talk. Thank you. I thank the speaker for the wonderful talk. It was very insightful, and I think we had a similar lecture by Professor Jasjeet Bagla in the morning on a similar topic. So we can proceed to the next talk now without wasting any time.
Okay, sure. So in the next talk, we have Sabora Zamani from Goldstone University, and she will be talking about gravitational lensing. I would request, I'm unmuting Sabora, pin number 10. Okay, you may share your screen now.
Hi, can you hear me well?
Yes, I can hear you.
So, okay. Hi, in next 10 minutes, I will try to explain gravitational lensing and some of its cosmological applications. So, gravitational lensing. One of the predictions of general relativity is that light does not just travel in a straight line, but its path is bent by gravity, and And the name of this phenomena is gravitational lensing. As you see in the picture, we have 4 images for one source. Technically, from the Earth, we can't see the source, but thanks to gravitational lensing, we can see the images of it at some other areas of the sky. This is another example of multiple images. Because of gravitational lensing, 3 distorted images of the same background galaxy and 5 images of the identical background quasar are seen in this Hubble view of galaxy clusters. In some special cases, if source, lens, observer are perfectly aligned and our lens is spherically symmetric, we have something that we call it Einstein ring, as you see in this simulation, but it's just a special case. We have 3 classes of gravitational lensing: strong, weak, and micro. Strong is the lens is a large mass, the geometry is favorable, the observer sees 2 or more separate images of the source. In which the lens is a large mass too, but the geometry is less favorable and the image of the source is mildly distorted. And micro, the lens is a small mass, usually a quasar, usually a star, sorry. So although the geometry is extremely favorable and source, lens, and observer are in a straight line, the deflection, distortion, and multiple images caused by lensing cannot be resolved. Instead, the image of the source appears to brighten for the duration of the lensing event. So, lensing geometry. I should note that I just wrote the equation in case later someone wanted to read, but for now, I just want to focus on the steps. There is simple geometric relation between the angles that we know as the lens equation. Here we have the lens equation for an ideal model. And by looking at the picture, we can write equation 1 by using angular diameter distance. And after that, we have just some simplification, and we have equation 2 and another simplification, like introducing some constant parameters for our lensing system in the lens and source plane. And after that, we can have the simplification equation in as a equation 3. So, as we said before, gravitational lensing has a lot of uses, like finding Hubble parameter and other cosmological parameters. We can test dark energy models. We can use it for dark matter studies and for determining large-scale geometry of universe. It can magnify distance object for us and acts as a natural telescopes. But for now, we want to talk more about measuring the Hubble parameter. The Hubble parameter is an important cosmological parameter that describes the expansion rate of the universe. But why measuring Hubble parameter is that important? One of the most important reasons is to solve Hubble tension. It's good to know there are multiple methods have been used to determine the Hubble parameter. Some of them is based on later universe and some of them is based on early universe. And gravitational lensing is based on later universe techniques. As techniques have improved, the estimated measurement uncertainties decrease, but the range of measured values has not, to the point that the disagreement is now statistically significant. This difference is called Hubble tension. Some of the range, as you see in the picture, are very different from the other ones, and that's Hubble tension. They are different kind of techniques. Today, estimates of the Hubble parameter based on phase and on the CMB radiation have uncertainty about 10%, and gravitational lens time delay measurements can produce some estimates that are less uncertain. But finding a convenient system has some difficulties, like different source regions magnified to different degrees, or uncertain lens distribution, or distortion due to perturbation along the line of sight. But it's better somehow. In the latest research for finding Hubble parameter from the strong lens system, the researchers suggested that the Hubble parameter is about 74. So we said that gravitational lenses offer such an alternative and potentially cleaner method. The principle is as follows. First, suppose the background source is variable. I mean, it brightens and fades. And suppose that at a given time, it undergoes a sudden brightening. This will, of course, mean that the observer will see each of the multiple images brighten. However, the light path which correspond to each of the multiple images will be slightly different because each path has taken a slightly different trajectory through the lensing galaxy. If we determine that image A has brightened one day later than image B, for example, this means that the length of the light path producing image A must be one light day longer than producing image B. In other words, this delay allows us to measure an absolute distance within the system, and that's related to Hubble parameter, and so we can find it. These are the steps to finding Hubble parameter. Again, I should note that I just wrote the equation in case someone wanted to read them. The first step is measure the light travel time, and that we have equation 4 for that. And the next one is measure and model the potential, and one of the really good models is the SciS. And the third step is infer the time delay descent, as we have equation 7. And the last one is convert into cosmological parameter. As you see, we have Hubble parameter in equation 5. So that's it. Thank you for listening.
Thank you very much for the talk, Sabura. It was very insightful. I would request the co-participants to ask any questions if they want to. If there are no questions, I would like to raise a question here, Sabura, if I'm allowed.
Okay.
You spoke about the changing Hubble parameter. So I wanted to ask, what is the criteria for change? As in, why does the Hubble parameter change in the first place? And what is the magnitude of that change over time?
I just don't understand your question so well. Could you pardon, please?
In one of your earlier slides, you had written that the Hubble parameter was measured in the early universe to be around 67, and in the late time universe, it is somewhere around 72, 73. So why do we have a change in this value? And what is the source of this change in the value of the Hubble parameter? And what is the magnitude of this change over time that we can expect?
I think that's, as I said, it's Hubble tension. That if you know why they are different, so you solve the Hubble tension. And I don't know, they are just different. When you use later universe techniques, the numbers are something, and early universe there are something different, and they're not matched. And they try to understand why, but not me at this time. And I said, if you know why they're different, that's you solve Hubble tension. I think if I have I will find better answer, I tell you later. And that's it, I think.
Thank you very much. Another participant has a question. Saurabh, you can go ahead.
Yeah. Hi, Sabura. I actually wanted to ask that you actually mentioned about this Hubble's parameter, how it is actually related into this lens equation. So I wanted to ask, like, are there any observational constraints onto how much we are able to distinguish the effects that Hubble parameter actually puts up into this Einstein ring system? As in, like, normally we not consider Hubble's parameter when we are trying to formulate some Einstein ring system, but when you're actually trying to uh, construct some systems, so are there any distinguishable features that we can see?
Yeah, I think they are, but I'm not in that field too much that I get any specific answer to you, but I think they are absolutely. That's it.
Thank you very much, Sabura. It was a wonderful talk. I think we can proceed to the next one.
Abhijit, you are not audible.
So again, I'm sorry for that. So the next talk we have is of Mr. Shubham Kala. We again have a pre-recorded video from his side. The participants can ask the questions after the end of the video. We can ask the questions to Mr. Shubham Kala. I will be sharing my screen now.
Good afternoon to all of you. Myself is Mr. Shubham Kala from Gurukul Kangdi Vishwavidyalaya, Haridwar. I would like to thank to organizing committee of AstroRetreat who gave me an opportunity to present my research work in this e-conference. Here I am going to deliver a talk related to my research work, and the title of my talk is Bending of Light Around a BTZ Black Hole. These are the outline of my talk. First, I will briefly discuss about the introduction part, including space-time structure, null geodesics, effective potential photon orbit. Then I will discuss the bending of light and variation of bending angle. And finally, we conclude in last section. This is the BTZ black hole space-time, rotating BTZ black hole space-time. Since we know that the BTZ black hole is a very interesting black hole because in 2+1 dimension there is no black hole solution without negative cosmological constant, and this black hole space-time have a negative cosmological constant, and the small l represent the radius of curvature, which is directly related to the negative cosmological constant. Since we know that without negative cosmological constant there is no vacuum Einstein field solution, because the Riemann tensor vanishes identically. And however, after taking the negative cosmological constant, we have the BTZ solution, and the metric given is in equation 1. The Labs function vanishes identically for the R, and this gives as the black hole horizon R plus, which is given by equation 2. Now, using the Euler-Lagrange equation, the generalized momentum for null geodesics can be written as in following form, where E is the total energy of test particle at infinity, while L is the angular momentum of test particle, and capital J is the rotation parameter of black hole. The equation 7 represent the effective potential of BTZ black hole. Here P plus and P minus represent the effective potential for direct motion and negative for retrograde motion, since both would coincide at event horizon, and this effective potential which is very useful to study the photon orbit, and it had been also studied in detail by the Cruz et al. Now it can be easily from the figure A and B. The effective potential increases as the value of radial distance increases, and it is also important there is no maxima or minima in both cases. Hence, it's mean that there is no stable photon orbit in this BTZ black hole. The left hand side figure represents the effective potential for direct orbits, and right hand side the figure show that the effective potential for retrograde motion. Now the figure show that is surface plot of effective potentials with radial distance and impact parameter B. The plot show that beyond the horizon there is the effective potential become constant, and there is no interaction of effective potential to the vertical plane, and we have only after taking the first derivative of effective potential, there is only one solution when the photon orbit exists, that is L is equal to B. It's mean the radius of curvature is equal to the impact parameter gives the photon orbit, only unstable photon orbit for BTZ black hole. Unstable means that is only dependent. There is after beyond the horizon the effective potential become constant and totally depend on the B. It's mean this is the unstable photon orbit. After some perturbation it will be goes out or circulate in the circular orbit. Now since it is very difficult task, it is not possible to convert the radial equations into Weierstrass form. Hence the expression of bending angle could not be obtained in terms of elliptical function. Hence we obtained the exact angle by numerical method, and the expression of bending angle is given as in equation 8. The parameter of using equation 8 can be defined as follow. Here C plus minus U plus minus gamma B have the sum value which is denoted here. The equation 9 represented the distance of closest approach, which can be easily obtained from equation 5. This will be very useful to explain the behavior of bending angle, and the figure show that the left one the variation of effective potential with respect to the inverse of distance of closest approach, and the right one is the variation of bending angle with respect to the radius of curvature, which is a function of cosmological constant. The figure left hand side figure show that there is a increase in bending angle when the distance of closest approach increases, and for retrograde motion this show that the diverse value or oppositely in the negative direction. This phenomena is known as the negative refraction, and the study of this phenomena had been done by the Akhlakia et al. And also discussed in the Nature article. And right hand side figure we can easily see that as the value of radius of curvature increases, the bending angle increases, and there are three cases. One is the solid line, second one is the dashed line, third one is dotted line. The solid line represent the condition when the angular momentum of test particle is less than the energy of test particle. In this case, the bending angle would be larger in comparison to other two cases, and in other two cases when the angular momentum of a test particle is equal to the energy parameter, then the bending angle would be smaller and towards to the no deflection region. Now finally we conclude that for external BTZ black hole we can have only photon orbit, and these photon orbit are unstable only for B is equal to L. We also found that the bending angle increases as the distance of closest approach of black hole is increases for direct motion, and also found that for a small value of cosmological constant, light goes closer to the black hole and the bending angle would be larger. It is also observed that the bending angle increases as the radius of curvature of black hole increases and takes maximum value when the square of rotation parameter of black hole is less than the square of energy parameter. In addition, for the other two cases, we already discussed about they toward to the shift toward to the no deflection region. Finally, we conclude that it will be an important study on whether a lower dimensional black hole affect the behavior of different parameter in comparison to higher dimension black hole. Now, these are the some references we have used in this paper. Now, thank you. If any query, then please ask.
Thank you very much, Mr. Shubham, for the wonderful talk. If there are any questions, then the participants are encouraged to ask them. Maybe we can proceed to the next talk, Abhijit.
Yes, surely. Just give me a minute. Okay. So for the next talk, we have with us Miss Sana. She's from Dr. Ruparel College, Matunga, and she will be talking about quenching of galaxies. So again, we have a pre-recorded video only. So along with that, we have Miss Sana with us. So I will be sharing my screen again now, and you will be able to view the video. I request Sana to not to share the screen. I will be sharing my screen and playing the video.
Galaxies are made.
Is it visible?
Yes, Abhijit, it is visible. You may go ahead.
Okay, thank you.
Up of billions of stars and also the hydrogen gas permeating between the stars so that we can make more star out of it. So the stars are nothing but the ball of hydrogen gas, and this gas is used by the stars to burn as a fuel. And when this fuel end, the star die. So when all the stars and galaxies are dead, and the hydrogen gas become useless for the star formation, then we say that galaxy is quenched. So our universe is only 14 billion years old, not so old to quench the galaxy. But then also we do see the galaxies which are red and dead. So what causing this galaxy to become quenched? So the answer is we have to provide some unfavorable condition for the galaxy to die. The first condition is to remove the stellar gas, and the second condition is to ignite the stellar gas. So if we ignite the stellar gas in which the molecules are not close enough, then this molecule get kinetic energy and the whole cloud will just flew apart, and the star cannot form. So throughout my presentation, I'm going to talk about the methods by which we can provide these two methods to galaxy. The first one is to remove the stellar gas, and the second one is to ignite the stellar gas. Now the first method is merging of the galaxies. So when the two galaxies are coming together under the influence of gravity, neglecting the influence of dark energy which causes the universe to expand, then no two star will collide, but the hydrogen gas between the star do collide, and whenever they collide we get shock waves. So the environment becomes so immense that it triggers the 100 to 200 solar mass of star formation, which is so huge. And this huge starburst causes the release of tremendous amount of energy, which is absorbed by the surrounding environment, and the environment become useless for the star formation. Now we are left with the red and dead galaxy. The second method is the environmental quenching. So we observe red galaxies are present in the group of clusters, in between the clusters, and the young galaxies are present in more isolated region. So there is some connection between the environment and the quenching of galaxy. So when we have a huge hydrogen gas cloud and then we simulate it, then we left out with the a web-like structure of universe in which we have filament, and when two filament intersect we get node and voids. So our Milky Way and Andromeda are present in void, while at node we have clusters of galaxy. And because of presence of so many galaxy and the gravitational effect, we have a hot molecular gas. So this hot molecular gas causes the four environmental effect, which further causes the quenching of galaxies. So the first effect is ram pressure effect. So suppose if you are moving on a bike and because of the surrounding environment your hair moves back. So in similar manner, because of presence of hot molecular gas, the cold molecular gas moves back. The second effect is thermal evaporation. So the hot gas causes cold gas to evaporate. Now the third is viscous stripping. So hot gas move faster than the colder gas, and because of this the colder gas moves away from the galaxies. Now the fourth one is galaxy harassment. So if two galaxies are close enough, then their gravitational affect the star formation of if star formation in another galaxy. Now the fourth method to quench the galaxy is morphology of galaxies. As you can see in slide that 90% of the elliptical galaxies are dead, while only 30% of the spiral galaxy are dead. So there is some connection between the morphology and the quenching of galaxies. So in the case of spiral galaxies, the spiral arm of the galaxy took away the colder molecular gases from the galaxies. So the second reason for the quenching of spiral galaxy is the central bar, center bar. So 30% of the spiral galaxies having the central bar. So this central bar funnels the cold molecular gases towards the center, and which causes the huge amount of starburst in galaxy, which further ignite the gases in the galaxy. So the galaxy quenched. Galaxy become quenched. Now the fourth and the last method of quenching is supermassive black hole. So active supermassive black hole are the one which are currently growing in Mars. They are taking material inside, and because of this they form the huge accretion disk around them, and this accretion disk are moving with such a high velocity and pressure. So this pressure can be released in the form of jets, and these jets are highly energetic. So this energy are absorbed by the surrounding environment, and we left with the red and dead galaxy. Now, if we simulate the formation of universe in the computer called star pipe, then we see that with supermassive black holes, we ended up having the less amount of less number of Messier galaxy, while without supermassive black hole we have a large number of Messier galaxy. So these are the methods to quench the galaxies.
Thank you for the wonderful presentation. I would like to request the participants to ask any questions if they have. Since I see no questions raised, I would like to thank the speaker. This talk was the last talk of the day, of the event rather. And on this note, I would like to end this session. And before I hand over to the ending note by Dr. Bindya and Dr. Venus, I would like to thank, on behalf of Stellar Universe, I would like to thank immensely the founder of Stellar Universe, Saurabh, who came up with this idea of organizing an online conference to utilize adverse times like these beneficially. This initial idea would have never become such a successful reality without Dr. Bindya Arora, whose active initiation and efforts brought the event to such a big stage. Without Dr. Bindya and the efforts of the entire team of SciRox and GNDU Amritsar, I would like to especially mention all my colleagues, Shankar, Ishita, Simran, Rishabh, Yatin, Abhijit, and many others whose name I am not taking due to constraints of time. I would like to thank all of them individually. Without even a single of your presence, I think this event would not have become such a successful event. We had participants from not just the country, but across the globe. We have participants from abroad too, and we had a range of talks and presentations in this. And I would really like to thank Dr. Bindya Arora and Dr. Venus and all their efforts, and to the entire team of AstroRetreat 2020. It's a pleasure to have worked with you all. And now I would like to request Dr. Bindya to say a few words in light of this. Thank you.
Thank you, Priyambada. And I would request Dr. Venus to kindly officially close the ceremony by giving a thank you note on behalf of the organizing committee. Dr. Venus, we cannot hear you, and your video is off as well.
I think this event would not have become such a successful event. We had participants from not just the country, but across the globe. We have participants from abroad too, and we had a range of talks and presentations in this. And I would really like to thank Dr. Bindya Arora and Dr. Venus and all their efforts, and to the entire team of AstroRetreat 2020.
Dr. Venus, I think
I've worked with you all, and now I would like to request Dr. Bindya to say.
the YouTube streaming is audible from your end,
Thank you.
but we cannot hear your voice.
Hello. Am I audible?
Yes, you're. Yes.
Oh, very nice. So should I present the thank you note? Hello.
Yes,
Hello.
sir.
All right. It's my immense pleasure to present a thanking note for the virtual conference on astrophysics and cosmology. AstroRetreat20, the name of the conference, which is organized by the Science Club of Guru Nanak Dev University and Student Universe, which is a student club of Delhi University. So this conference provided an opportunity to the students and young physicists to learn systematic developments of those areas of astrophysics and cosmology, which are essential for proper understanding of challenging problems of the contemporary times. It was clearly reflected in the quality of the invited talks, audio and visual, and the poster presentations from the students from undergraduate to PhD level during the conference. I must say, all the presentations were fantastic. It is wonderful to see students coming together and organizing such a conference, as it enriched us about astrophysics and cosmology. It must have helped them in learning how to organize or how to do event management. It is a very, very good thing that you are doing this so young. It will help you later on. I'm sure this event will become a landmark, a benchmark of how to organize virtual conferences for other student bodies and as well as for other educational uh, institutions. In the end, I would like to thank our Dean Academic Affairs, Dr. Sarabjot Bahal, and Dean Student Welfares, Dr. Hardeep Singh, for inaugurating the conference. And we are really cherish the presence of Professor Saini and Professor R.C. Singh in the beginning and during the conference. We are very thankful to Professor Deshpande and Professor Bagla for accepting our offer to deliver these lectures. We are grateful to all the students who have worked continuously and very hard to make this event a successful one. To name a few, Saurabh, Ishita, Rishabh, Simarpreet, Shankar, Priyamvada, Abhijit, Preeti, and Yatin. We are really thankful for your efforts. We are thankful to our Vice Chancellor, Dr. Jaspal Singh Sandhu, for continuously supporting us in these efforts. And in the end, and the most important, a very big thank and congratulations to Dr. Bindiya Arora, who has put in such a hard work and worked tirelessly to convene this meeting. We hope she will continue to organize such events for our science club in future as well. Thank you.
Thank you, Dr. Venus. I would also like to thank the advertising partner, Secret of the Universe, for their support in advertising this conference. I would like to end the conference officially now here, and thank you all.